因为我去楼上 set 了，
嗯，
我去楼上我的 account 全部 set 了，重新做一次。这样大家就方便，好像我这个给 PJ 的，换其他的房间都不知道。
啊，你是先给谁这个？
我的 set 把那个去 P，因为我没有放在 desktop 嘛，等下 PJ 他的方向做。
The YouTube versions on YouTube.
Yes.
There are teachers there, but I mean, it's not necessarily good now. But yeah, there's one in the biggest room that I saw one, is in my room. Teachers are in the box somewhere and so. But then, we might distribute later, but yeah.
Então, Downloading the slide for this room.
Oh yeah, that's great. No, I was trying. Do you know where Rayhan is?
No idea. You need me to call him?
No, I'll just look around and I'll.
Are you the session chair?
Yeah.
Oh, I'm the volunteer. So
nice to meet you.
nice meeting you. I just wanted to make sure you know.
Okay, sounds good. And so maybe the presenter can use the uploaded slide here in the.
Yeah, they recommend that everyone uses the uploaded slides, but there's two people where it was gonna say they want to use their own laptops.
Okay.
But we have to like connect it via HDMI or and then make sure they're on the Zoom.
Mhm.
But I think as long as
Alright.
I think yeah, and then I think as long as like they don't require audio, then they can just connect to the Zoom.
Okay,
Like
sounds
that. But otherwise we have HDMI and we can
Mhm.
use it.
Okay, this is my phone.
Yeah, and I think this is to like take off this lanyard
I see.
and then put on the microphone. You know, if there's like a mic you'll need to pass around for Q&A.
I'm not sure, but maybe. So, the question, so maybe the speaker can use this microphone, but is there?
There are questions and
Yeah.
statements. Yeah, I know at least like last year at Splash, they had like an extra microphone, but I mean, I think as long as the audio, excuse me. I think as long as the audio shows up on like the Zoom and it's registering it, then we should be okay.
Okay,
Um,
so maybe the speaker should repeat for the questions or?
yeah, that sounds like a good idea. Okay.
Okay, great,
Right.
thank you.
Hello, hello.
Hi.
Today.
Yeah, so good.
That's.
Yeah.
Yeah.
Thank you for the, asking the invite to here. Yes.
Not to me. I
Yeah.
was actually wondering, because I cannot speak for 90 minutes, but the program says the whole session is 90 minutes. So you could change it to 70 minutes if it's not too late to change it.
If you are extending the conversation then, the timing, of course, we can, if all the questions are ready, then we can go to the later.
Okay,
that's okay.
yes, yeah, sure, yeah, because 90 minutes is a lot.
Okay, yeah, I see.
Yeah. I see, because in this, like, the whole session is 90 minutes, right? So
Yeah.
for other programs, the same. And then they mark that, everything.
I see. Yeah, no problem. Yeah.
It's fine.
Yeah.
Let's see, maybe I can talk.
Yeah,
And talk.
I understand that 90 minutes the two. Yeah, sure, yeah.
Yes, and I'm sure audience will also.
Yeah, thank you.
Yeah, exactly.
Easy.
Yeah, I heard you started already.
Yeah, yes, unfortunately, I get one paper, but it's not one. No problem. I forgot about,
Yeah.
Yes. Yes, no, it's
No, yeah, this year.
Okay, so it's all around, so maybe.
Yeah.
Yeah.
Great.
Yeah, most of the masters.
Great.
Yeah.
And now, SR3. Is this one? No, SR2 should be on site.
In 5 or more years.
Oh, okay.
Yes, and then graduating.
Okay, so it's
So start for next year.
Yes.
Yes. I don't know, but I could try the audio.
So. Okay, so this is the machine line. So I think your flight is a very long from
It's 24 hours. Yes, because I had a layover even. So it's 5 hours to Vancouver and 2 hours layover and then 60 hours. Right?
Yes.
Extremely long.
That's very long.
Extremely tired. This might. We have also tried.
Okay.
No. I have this specimen.
Yeah. You can use this one.
Oh, the.
Okay.
Oh, did you?
Not sure you are what's in how.
I see.
I see it. Okay, thank you.
Yes. It makes sense.
Yeah, it's fine.
You have the corresponding part of the comments.
Yeah.
Which is, I cannot, I think I don't have the, in this.
Oh, yeah. Yeah. Oh, that's it. I did it. Have the,
Yeah, yes.
yeah. It's not the shit. Look the big share. This is.
And my first name is, okay. I
Oh,
don't have this. It's.
Yeah, okay.
Yes.
Okay.
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 Really.
So then the English pronunciation.
Yes. Let me see, it's possible. This is really hard.
Yeah.
Yeah. Yeah, are you able to join with, is that you?
Okay, I need to join the Zoom, to share the.
Yeah, there's like a link over there, yeah. Yeah, so if I find any links. Onto this. If you share your screen from your Zoom link, then we can, everyone can see your stuff.
The AC is broken outside. The AC is broken outside.
Yeah, or not.
No, I heard it.
I'm not sure how to detect this computer, but what you can do is if you
No.
okay.
I think I got it.
Okay.
Yeah. Okay.
Okay, I'll extend as on my laptop. I think I think connected by HDMI.
Yeah, that's the one. So-
Yes, here, I'm running around.
Yeah, that's about it.
We go to the to eventually get it, just direct it.
Yeah, I think
It was not that.
Run through
Let's check what the
push pins.
Yeah.
Do you want to push pin or?
No, I want to get the settings one for this. Because I'm connected to HDMI, I should be able to see the settings one.
Surprised to see that there are no signs.
No, not the
What's it?
one.
You need your own screen.
No,
Oh, that is
Yeah,
for
yeah,
your
yeah.
screen.
No,
It wasn't-
to do a second to play, she does an external monitor.
I think then
I didn't see them.
mirroring.
It's saying it's here. So.
I just took it.
This is easy or something.
No, I think it's there's only.
Family settings, DC. Oh, first,
What kind of service?
yeah.
Single.
Single, just right.
Thank you.
Because it was actually
Someone else.
easy to find, like the way it's.
Uh-huh. So you want to show the.
Well, we should still have it. An alternative is like if we. I don't know if that's like an option for you, if you can have this work. How do you think you know? Oh, not. Oh, okay, no.
So basically this laptop is desktop. There's console over here.
Oh,
I see.
oh.
I thought what's the. Okay, yeah, no.
Yes.
Yeah, I'm sure.
Yeah.
That's how it works. You don't need to do it.
Well, but then forever.
Seems like a ridiculous thing to not try for 3 months. Yeah. Like.
Okay, so I think we are ready to start. Yeah, good morning, everyone, and thanks for joining the HOPE workshop. And I'm Taro, co-organizing HOPE workshop with Guilherme. So I'm very happy to see you in all, and both in person and perhaps online. And as one of the co-organizers, I'd like to start by thanking all the authors submitting their great work and for the reviewers who helped us make this excellent program. So we hope you all of you will enjoy the HOPE workshop and every talk and discussions and chance to exchange ideas. Yeah. Okay. So thank you for joining us, and let's start the first talk. And the first talk is invited speaker and by the Nining Xie from University of Toronto. Yeah, Nining.
Thank you. This one? Are you worried? Oh, here. Right. Hello, everyone. I'm Ning from the University of Toronto. It's an honor to be here to give a talk on my recent work on smart handlers handling the selection monad. This is joint work with my collaborator, Golden Plotkin. So this talk is going to be about decision-making processes. So whether you like it or not, we make lots of decisions every day. For example, whether to drink coffee or tea for the breakfast, or which password to use when you set up an account, or whether you would like to accept or reject a specific paper if you serve on a conference program committee. And it would be really useful if we can model this kind of decision-making processes as programs, so that we can express decisions as computations and we can program with them and reason about them. And in order to do that, we would need the program to be able to express decisions as choices and capture consequences of choices, and then based on the consequences of choices, define optimization strategies. As a concrete example of such kind of decision-making programs, consider implementing a binary search algorithm that searches an ordered array A for a value X. And this slide shows the type signature of the program, where B search takes a value X and an ordered array A and the ranges of the array to search for left L and right R. And for simplicity, we would assume the value is always in the array, so the searching is always successful. And hopefully you still remember how to implement this algorithm from your algorithm courses. So the program would go like this. So first, for each iteration of the program, we would split the array into two halves. And then we compare the element at the middle of the array, AM, with the value X. If AM is equivalent to X, great, we are done. Or otherwise, depending on which value is smaller, we will do a recursive call to B search with updated range from M+1 to R if AM is smaller, or otherwise from L to M-1. So in other words, the essence of this algorithm is that for each iteration, we compare X with a specific element at index M to shorten the range of the array in which searching must be performed. And a natural question to ask then is, which index M should we actually use for each iteration? And in this case, we have always used the element in the middle of an array, but this is actually really a choice that we can make differently, right? Like consider, for example, if X is really, really small and the array contains a lot of large numbers, then maybe for each iteration, we can be a little bit more aggressive, smaller indices, so that we can perform fewer recursions to get more efficiency. And in order to capture this kind of choices, smart choices is a set of APIs basically used at Google, which can be used to implement binary search like this. And these APIs, they allow programmers to provide choices, contexts, and feedback to the underlying server. And in this case, the choices are basically an integer number from the range L and R, and the contexts include the value X and the values of elements at both ends of array. And the feedback is basically the program has to pay to recurse. So the underlying server should learn to perform less recursions in order to get better optimizations. And in this particular case, we would expect the server maybe to perform some training and deploy policies for making decisions in order to avoid payments. For example, a clever choice can take into account the distribution of the data and the records of past decisions in order to decide how to better select the M for each iteration. But this is just a particular set of APIs. And in this talk, we would like to study this kind of decision-making abstractions using a more general approach and from a PL perspective. More specifically, this talk is about the marriage of two programming language features to support two key components in decision-making processes. First, there may be numerous choice operations in a program which can depend on various context information, complicated computations, or maybe even one choice can depend on other choices. So we need a way to express composable and modular user-defined operations. In order to do that, we use algebraic effect handlers, which allows for choice operations to be defined as user-defined operations that can be then handled separately using effect handlers. And at the same time, we also need to model computations that involve making choices. So we take ideas from a monad called the selection monad, which enables handlers to choose computations based on the losses the potential choices entail. And we call the resulting effect handler systems smart handlers, as these smart handlers empower programmers to write decision-making programs using choice operations, which can then be handled separately by applying different optimization algorithms implemented as handlers. So for the rest of the talk, I will first give a taste of smart handlers through an example, and then I will define a model calculus that defines the semantics of our design. And finally, we will see some more examples implemented using smart handlers. And let's start with a taste of smart handlers. To do that, I will first provide a brief background on algebraic effect handlers, and then I will show how the selection monet can be added to the system on top of effect handlers. And we start with the background on algebraic effect handlers through a simple example. So intuitively, effect handlers are a powerful way to incorporate computational effects in a programming language. And for this particular example, we consider an effect signature that defines an effect operation decide that takes a unit and returns a Boolean. And with this effect signature, we can already start programming with these operations. For example, we can write a program F that performs operation decide, and in this case, twice. Specifically, F performs the operation decide by providing an argument to this operation, in this case, just a unit. And F performs effects twice and returns the result of the AND operator taking these two variables. And this program has no idea at all how decide is going to be actually implemented, because the semantics of effect operations are actually provided by effect handlers. So we write this with handle class to handle the computation F using a specific handler, in this case, a handler for decide. And the handler defines what happens when an operation is performed. In this case, decide maps to a function that takes the argument to the operation, in this case, just the unit, as well as a continuation that captures from where the operation is performed to where the handler is used to handle this operation. And in this case, the handler performs the continuation k twice with true and false respectively and concatenates the result. And the return clause is applied when the computation returns normally. So in this case, if the computation returns a result X, then the return clause simply wraps the result into a singleton list. And that's why also the return type of K is a list of Boolean now. So if we actually run this program, we would get a list with 4 elements: true, false, false, false. That corresponds to the case when X is true, Y is true, and X is true, Y is false, and X is false, Y is true, and X is false, Y is false. And only the very first element would be true. So I hope this example provides an intuitive explanation about effect handlers, where the syntax and semantics of operations can be decomposed and defined separately, so that we can do more modular programming, where we can, for example, write a set of operations in a single program, or we can nest the effect handlers in different orders to handle operations in a program. So with the background of algebraic effect handlers ready, we can now demonstrate how the selection monad can be useful. And let's demonstrate that by considering another example. So imagine we are registering for an account at a website where we need to set a password. And of course, there is a set of criteria for the password, but those criteria are not very important for our example, but they are just there. And let's consider that we want to model this process of picking a password as an effective program, with the idea being that we want to define an operation pick that takes a list of password candidates and returns the chosen password. And with this effect signature, we can now already start performing the pick operation in our program. For example, maybe we would like to pick a password from this list of 3 candidates: Hello World, ICFP 25, and Singapore. And of course, as with effect handlers, the program does not know how this pick operation is going to get handled. But very importantly, the program wants the handler to know that there is certain losses associated with each choice, or costs associated with each choice, right? Like, for example, maybe we want the password to be as long as possible. So depending on the length of the password, we would incur a loss, which is a negative result of the length of the password. So a negative loss can be considered as a reward, right? Because losses are due to rewards. So we are basically rewarding longer passwords. And maybe also we want the password to contain as many distinct elements as possible. So there is some Haskell functions that calculates how many distinct number of characters there are in a string. And then it also incurs a loss, which is the negative result of I squared. And the hope is that, the handlers can take into account those loss informations when it makes the decision for which password to use. And here, the loss operation can be considered as a built-in operation that basically corresponds to a writer. So we are writing to the handler what losses that will occur for each operation, for each choice of the password candidate. And then the program can just return the password that is chosen. Now, let's try to define a handler for pick. And of course, we can define different handlers. And here, let's consider a greedy algorithm that picks a password from the list that minimizes the loss. So let's try to implement the handler. So in this case, the handler for pick will receive the list of strings as PS and then the continuation K. And we can start by filtering out those passwords that do not satisfy the criterion, right? But again, those set of criteria do not really matter for our example. But now we have a problem, which is what happens afterwards, or how can we actually implement this handler, right? Because to implement our desired semantics that we would like to make a decision to minimize the loss, we would first need to know the loss associated with each candidate. But we do not have that piece of information available when we define this handler. And this is how the selection monad comes into play. And the selection monad basically models computations that involve making a choice. And this slide gives the definition of the selection monad. So S of X is basically a higher order function that takes a selection from X to R and returns an X. And the interpretation of this monad is that if you can tell me how X affects R, then I'm happy to pick an X for you. And we can consider some of the examples that maybe you have encountered in your program, based on your programming experience. For example, argmax is a function that has this type. And argmax basically returns the arguments at which a function output value is maximized. And you can also consider an operator called exists that tries to find at least one element that satisfies the function x to r if r is, for example, a proposition or a Boolean value. And if you are familiar with continuation monad, maybe you have noticed some similarities and differences between selection monad and continuation monad. And in the case of continuation monad, the monad will go from x to r, and the selection monad goes from x to r to x, because in the continuation monad, you care more about the final result of the continuation, while in the selection monad, you care more about which element we have selected. And of course, if we have the elements available and we have the selection function, we can still recover the final result of the computation. And if you know continuation monad, of course, you know continuation monad is a monad. And the selection monad apparently is also a monad. And to show you that this is the case, let's actually try to define the return function and the bind function for the selection monad. And one advantage of programming with types is those definitions are basically very straightforward if we just follow the type signature, and there are basically no other choices we can make in this definition. What do I mean? So let's look at those definitions and try to first define the return function for the selection monad. So the return function has this type signature. It takes an x and returns sx. So let's define the definition of return. Of course, it is a function, so we know it takes an x. And it needs to return something of type sx. And we know sx is x to r to x. So we have another function, gamma, with type x to r. And now we need to return x. Then what should we return? There are no other choices, right? We will just return x. And the bind operation is slightly more complicated. So in this case, the signature goes from sx to x to sy, and it returns sy in the end. But again, let's just follow the type signature and try to write out the definition. First, it is a function. So we have capital F of type sx and this little f of type x to sr to sy. And now we need to return sy. And sy is the function from y to r to y. So we know that we are going to have a gamma y to r, and our only job left now is to construct a y. We know how to construct the y because we have f available, and f is the only function that returns the y in the end, right? And we can apply f as long as we provide it with a value x and a function from y to r. And we do have the function from y to r, which is gamma, and now we only need to construct x. And looking at the context, the only way we can construct an x is calling this big F, as long as we can provide a function from x to r. Since it is a function, of course, we can take an argument of type x and now just need to return r. And the only way we can return r is by applying gamma if we can provide a y, right? And now we are back in the situation where we need to provide a y, but in this case, we have an x available already, so we can just call f with x as well as the function gamma from y to r. So as you can see, right, following the type signature, we can write out the definition very mechanically. And although the function might seem quite complicated, the intuition behind this is, right, this function is basically just trying to get a loss value based on how x affects y. And this is how the selection monad trains a list of computations. And more interestingly, we can also combine selection monad with other monads. And for example, we can combine selection monad with the writer monad, where the writer monad is just the standard pair of r and x, where this r is the same r as this x to r. And this writer monad basically provides semantics for our loss operations. Like, as I said, this loss operation is really a writer operation that tries to write and accumulate losses. And our final selection monad that we actually use in our semantics is slightly more complicated than this, because we also need to take into account the set of effect operations that are not handled because we are working with effect handlers. And we'll get back to this definition when we talk about selection, when we talk about the denotational semantics, if we have time. All right. So now that we have introduced the selection monad, we can actually go back to our definition of the greedy algorithm for pick, and let's try to finish it by applying ideas inspired by the selection monad. And the key idea now is in the operation clause, in addition to the argument PS as well as the continuation K, the handler now receives another continuation L, which we call the choice continuation. And if you compare the choice continuation with continuation, you can see that they both accept the return result of the operation, but different from continuation, choice continuation always has the return type a real number, which denotes the loss associated with the choice. And if we have this choice continuation available, then we can continue writing the definition of the handler, where we basically just call this mean width function, which takes the function and a list of arguments and tries to pick from the list of arguments a value that minimizes the function L. And once we have picked the password, then we can just resume the original computation by calling f with p. So this is basically the handler we'll be using for picking our password. And a particular thing worth noting is that in this system, we actually have two continuations, right? So we have this continuation k that is delimited because it captures from where the operation is performed to where the handler is used to handle this operation. And we also have the choice continuation that L, which is global by default because it calculates how the loss affects the rest of the whole program. But of course, we have also provided additional language constructs that can help you delimit the scope of choice continuation if you want. So we actually have a more general setting where the continuation is global by default, but can be delimited if you want. And the continuation k is basically taken from standard effect handlers, right? And the choice continuation is the new continuation that corresponds to computational ideas derived from the selection monad. And we can also look at the types of these continuations, and we can observe similarities and differences. So if the operation is an operation that goes from A to B, then the continuation would have type B to the type of the program, which is the type of the whole handler program. While for the choice continuation, it would always go from B to a real number because the choice continuation is supposed to tell us what loss is associated with each choice of the operation result. All right. So I hope that gives you a rough feeling about what we can do with smart handlers now that we have this loss information available. And before we see more examples, let's look at a minimal model calculus that defines the semantics we want of our design. So we will start with syntax. And the syntax of the expression includes, well, constants and primitive functions, and also constructs that correspond to a lambda calculus. We have variables, we have functions, and we have applications. And because we are working in an effect type system, so the lambdas are explicitly annotated with effect annotation that tells us what effect can occur in the body when this function is applied. And we have three constructs associated with effect handlers. So we can perform an effect operation op by providing an argument E. And we can also call the loss operation by providing an argument E. And we can also handle a computation E using a specific handler H. And as I said, this loss operation is basically just a writer operation that writes the loss. So if you call the loss continuation multiple times, the losses will get accumulated. And we have three constructs specifically for ideas inspired by the selection monad, where this first form is really just an internal form that occurs during evaluation. So this is not a user-facing syntax, but it is very important that gets us the semantics right when we evaluate a program. So we would pronounce this triangle operator as then because it basically accumulates losses. So it will first evaluate E1 and then collect the loss of it, and then pass the result of E1 as X to E2 and calculates further losses from E2. And the last two constructs are the scoping constructs that we use that can be used to delimit the scope of losses and the choice continuations. And we'll get back to them when we talk about the operational semantics. And we can also define loss continuation expressions, which are basically loss continuation expressions corresponds to the function from X to R in the selection monad definition. So it takes a value and calculates a loss. So it only has two forms. It is either a zero loss continuation, so evaluation of every program will start with a zero loss continuation, or it is extending a loss continuation with another loss continuation expression. And this extension will happen during evaluation so that we can capture the loss information for a particular program result by extracting information from the rest of the program. And we will talk more about how those constructs are built and extended when we talk about operational semantics. And lastly, we have the syntax for handlers. And the syntax for handlers is mostly standard, except that the handler classes, the operation classes now can take this additional choice continuation as an argument. And a handler might handle multiple operations and define an optional return clause. And in this case, the syntax is a little bit verbose just because we are programming with explicit types and effects. So everything has explicit effect annotations that tells us, for example, what effect might occur when a function gets applied. But all those effect annotations are not that important to our operational semantics. And this is the complete set of syntax, right? We have basically expressions corresponds to the lambda calculus, to the effect handlers, and corresponds to things that we can use to manipulate losses and choice continuations. And with the syntax ready, we can now talk about the type system and the operational semantics. And the type system is mostly trivial. It is just used to make sure the system is type safe. And the operational semantics will be more interesting where we see how those loss continuations are built. So let's start with the type system. So as I said, the type system is actually quite straightforward. So we have base types or a function type. And for a function type, it goes from sigma to tau. We need to record what kind of effects that can occur when the function is applied. And the effect epsilon is a set of labels, so it can either be empty or we can extend epsilon with an additional label L. And we have the normal typing context that tracks the type of variables, and we have a global operation context that defines what operations and what their types are for each effect label. And the typing judgment is just like the typing judgment for any effect type system, where under the typing context the this expression E has type sigma and might perform effects in epsilon. And all these the 5 rules on this slide, they are very standard typing rules for the lambda constructs in effect type system. And one particular thing that might be worth noting is again, because we are working with effects, the function type needs to track the effect of the body. So if in this case E can perform effect in epsilon, then the return function type will need to remember that the function can perform epsilon when it is applied. And we'll skip all the other rules because they are fairly standard, and let's get to the slightly more interesting ones about effect handlers. So we have 3 rules corresponding to the effect operations, right? We can perform an operation op by providing an argument E. And if we perform operation op, then we should record in the returned effect epsilon that we have performed this operation op that corresponds to the effect label L. So this set condition makes sure that L does appear in epsilon. And on the other hand, when we handle an expression using a handler, then the handler can eliminate one effect label from the effect information of the expression. So if E has effect epsilon L, then after E is handled, then the effect left is just epsilon. And the loss operation takes a real number, which is E, and itself just returns a unit because its job is just to record this loss information, and it has whatever effect that this E says it has. Right. We get to more interesting typing rules when we talk about constructs corresponding to the selection monad, right? For example, we want to type check then. So as I said, then works by first evaluating E and then pass the result of E to E2, basically binding the result of E1 to X when type check E2. So E1 has the same type as X. And local works similarly. So this E has this type epsilon, which is going to be passed to this loss continuation G that will take the result of E and calculate the loss L, the loss R. And all those set conditions on the effects, they are basically just needed for type safety. So we will not be worrying about effects too much when we talk about operational semantics. So this is just to show you this type system exists. We have typing rules corresponding to each language construct we have in the tag types. And our last typing rule is reset. So reset just slightly changes the semantics of E, but in terms of typing, it's very trivial. It just has the same effect and type as E. So like I said, this type system is mostly trivial. We just need those typing rules so that we can prove type safety of our calculus. And it's a very standard type system as most effect handler systems. And the more interesting bit is actually in the operational semantics of these effects. And the operational semantics is also one of the most complicated bit in our system. So this is how the evaluation judgment looks like. So it reads that under the loss continuation G, E evaluates to E prime and producing a loss R. And the actual operational semantics is actually also associated with effect information. But from now on, we will be just forgetting about all those effect informations and instead focusing on the behavior of the program during the operational semantics. And intuitively, this loss continuation G corresponds to that function X to R in the definition of the selection monad. And this is how our semantics is built. So let's now look at some of those operational semantics rules that maybe help you understand a bit better and deeper about how this system is working. So we will start with two standard rules. If we want to evaluate a primitive function f, then we will assume some built-in evaluation rules for f. And evaluating a lambda applied to a value is just one step of beta reduction with a substitution. And both rules, they just have zero loss, right? Because there is no loss to be reported. And the language construct that will start building loss from the beginning, right, is the loss operator that takes an expression R. And in this case, we are focusing on when R is already a value, but of course, our system has all those congruent rules that evaluate expressions on the evaluation context. So if R is already a value, then what happens? Well, the return type of loss is just a unit, so we just return a unit. But we would remember that we have produced this loss R in the operational semantics by keeping track of this R in the operational semantics. And this is basically the only rule that produces loss, and the loss will keep being propagated throughout the evaluation of our program. But this is the only construct that could produce a loss value. And we would omit lots of other evaluation rules, but let's focus on the most interesting one of this system, which is the evaluation rule for handlers. So if we want to evaluate this computation E under this handler H, then what should we do? Well, it depends what happens with this E, right? Because there are three cases. Maybe E returns a value already, or maybe E performs operation that needs to be handled, or maybe E itself sets, right, under the handlers. So we will have to define three operational semantics rules corresponding to each of these three cases. Let's start with when E returns a value. So if E returns a value, in that case, we will just get the return clause from the handler. Let's say it is VR, and we just apply VR to V. And we also produce a zero loss because there's no loss produced with this step of evaluation, right? And more interestingly, what happens if E performs an operation? So this is the actual very important bit in the semantics that gets us the choice continuation and get our examples to work. So if E performs an operation, and in this case, we are trying to find the handler that will handle this operation. So we write this capital K as evaluation context that sits between where the operation is performed and where the handler is, which is the handler that we use to handle this operation. And there are side conditions that make sure that we use the innermost corresponding handler for this operation, because you might have multiple handlers for this operation, right? And we want to use the innermost one. And once we have found the innermost operation, innermost handler for this operation, we just get the operation clause, in this case VO, and we apply VO to 3 arguments. V is the argument we provide to the operation, and L is the choice continuation, and K is the continuation. And of course, we need to define what K and L are, right, for this rule to work. So intuitively, K corresponds to the standard delimited continuation for effective handlers, where we capture, again, from where the operation is performed to where the handler is used to handle this operation. So it just resumes original computation once it receives a return result Y. But an additional bit of complexity in our system is that we actually needed to do a little bit wrapping around this continuation, because we do not only need to remember, we do not only need to capture the continuation, but we also need to remember that this continuation is captured under that loss continuation G. So this bracket is one of the language constructs that helps delimit the scope of choice continuations. In this case, we just want to remember that this expression is captured under the loss continuation G. So whenever we resume this computation, that reception should be evaluated under the loss continuation G as well. And the choice continuation, right, is one of the most important bits in the operational semantics. It looks very similar to the continuation. But instead of local, it uses this triangle operator to actually calculate the loss of the continuation that is associated with the operation result Y. So if you give me a loss, give me operation result Y, then I will use this Y to calculate what losses will occur in the rest of the program. And of course, I need to do a little bit more because this program is evaluated under the current loss continuation G. So I also need to pass the result to the loss continuation G, actually calculate the loss. So intuitively speaking, this is how we calculate the loss associated with each operation result. And we still have the last case, which is when E steps under the handler H. And normally, right, if E steps E prime, then of course with H handle E will evaluate with H handle E prime. But an additional complexity in the operational semantics rule is which loss continuation should we use to evaluate this E? We know that this with H handle E, this whole expression is evaluated under the loss continuation G, which is waiting for the result of this expression. But the G is not waiting for the result of E, right? Because when E returns, we know that the return clause of the handler will get applied first. So that is why we need to extend the loss continuation when we evaluate E. So the loss continuation under which we evaluate E is not G, but it is first applying the return clause VR from the handler, and then we pass the whole result to G that is actually waiting for the result of this whole handle expression. And you can see this is how the loss continuation gets extended during evaluation of the program. And our last bit of complexity in the operational semantics is just to define the operational semantics for them. right? What happens actually when we call then? So intuitively, then is just accumulating losses. So if we evaluate E, if E steps to E prime and produces a loss R, then this rule must accumulate the loss that is produced by E by evaluating this E. And of course, E prime still needs to get evaluated under G prime. And the semantics, this rule itself produces a zero loss because the whole purpose of this then operator is to calculate a loss value for the operation, and itself does not incur any loss. And if E already reduces to a value in the end, then we would just evaluate this E by passing the value of V to E by binding it to X. And again, because this whole thing just produces a zero loss, we put this local construct. Remember that this whole thing produces zero loss by itself, because the whole purpose is just to calculate a real number that actually represents a loss. And lastly, we have the rule for local, and it's actually very intuitive. So if we want to localize a loss continuation for G, then that just means we will change under which loss continuation E is evaluated. So it changes from G to G1 in this case. And if we want to reset an expression, that just means the loss information from E will not be propagated to the outside. So this expression in itself always produce a zero loss. Then this allows us to localize loss information. And that's basically all the operational semantics rules, right? All the most important ones. And as I said, of course, we have more rules that will evaluate things under evaluation context, but these rules have captured the essence of our system where we handle operation with the handler, and we talked about how the loss continuation gets extended during evaluation and how the then operator accumulates the loss information. And with that, we can now go back to our example of picking a password and actually see how this program gets evaluated. So we would always start evaluating expression under a zero loss continuation, right? So let's assume this whole program is evaluated under zero loss continuation. And we are evaluating a program under a handler. And the first statement we need to evaluate is this pick operation, right? And because we are performing an operation, this is where we should apply the handle rule that handles this operation. And if we want to handle this operation, we will get the operation clause of pick from the handler and bind PS and L and K. So in this case, I have also put the dimension of K and L on the bottom of the slide. So we will start by filtering out the passwords that do not satisfy the criterion. And again, this specific criterion do not actually matter. And in this case, let's assume you always need a special symbol in your password. So let's rule out Singapore first. And then PS prime is just the hello world and ICFP 25. And we can now call this function mean with the loss continuation L and the two candidates hello world and SFP 25. And the implementation of mean with is basically just enumerate all the choices, right, and gets the element that minimizes the value of L. So let's start by enumerating all the choices we have. So in this case, we have hello world and SFP 2025, and let's start with hello world. So if P is hello world, right, and now we can actually evaluate the loss continuation and try to see what loss value we would get in the end. And in this case, the handler H doesn't quite matter, so let's just ignore it. And then we calculate the loss value. And the first value we would produce is the length of P, or the negative of the length of P, right? And this whole thing is still evaluated under this right triangle. So we need to apply first the then rule that allows us to accumulate losses. And in this case, the length of P, or the negative value of it, is just -12. And then we keep evaluating the rest of the program still under the same triangle operator. And our second loss is just the square of how many distinct characters are there in a string. So I have done the calculation for you, so you can trust me on that. And then we just need to calculate the final string. And in this case, the loss value is just 0. So the final result would be minus 12 plus minus 81 minus 0, which is minus 93. And this is the loss we would get when P is hello world, right? But we also have another option, which is when P is ICFP 25. So I have also done the calculation, and in this case, if P is ICFP 25, then we will get minus 8 plus minus 64 plus minus 64 plus 0, which is minus 72. And we compare these two loss values, and we realize, the loss for hello world is lower, so we should resume the original computation with P being hello world. And if we resume the original computation with P being hello world, then we can produce the final result, which is password is hello world. So hello world is the safest password, right? You should use when you register account. And this whole computation, of course, itself produced a loss minus 93. So this is an example where we make use of the choice continuation to allow the handlers to actually pick a particular password based on the loss information, right? And now let's see more examples and what other things we can do with smart handlers. And so in the case of picking your password, right, we basically just enumerated all the choices and then try to get the one that produced the optimal result, because we are applying a greedy algorithm, right? But in practice, of course, it's not always possible to enumerate all the potential choices and identify the best one. So we look at another example for optimization algorithms, and we consider the simplest form of linear regression. For linear regression, basically, we want to find a linear relation between two variables given a data set of x and y, right? And if we have this data set, then the goal is to find a weight w and a bias b so that the linear function best models this relation. So in this case, I have x being the novelty of your paper and y being the acceptance rate of the paper. And of course, the data is completely made up. So we can represent this linear regression problem, right, as an optimization program in which we can gradually refine the parameters by applying optimization algorithms. So what we will do is we will start by defining operation optimize that takes the current parameters and returns the updated parameter. And similarly to our set a password example, with this effect operation, right, we can already start programming with this effect operation. So let's try to define the program that does linear regression with respect to the current weight w, bias b, and a data point x and y. And we will co-optimize by passing the current parameters w and b, and somehow we expect optimize to return the updated parameter w prime and b prime. And if we have the updated parameter, then we can actually calculate the predicted y prime using those parameters and x, right? And now any differences between y and y prime is the corresponding loss for this parameter. And in this case, is the square of the difference of y and y prime. And once we get, we have passed the loss information, then we can just return the updated parameters w prime and b prime. And now a more interesting question right now is how this optimized operation should be handled. So we would like to apply optimization algorithms simply by defining handlers for optimize. And in this particular case, we would apply a stochastic gradient descent which is a widely used method for iterative optimization. And the idea is basically starting from some initial parameters. The gradient descent would minimize a cost function by repeatedly updating the parameters in the direction opposite to their gradients. And we can do this step after processing each randomly selected data point. So now we can implement gradient descent as a handler. And this handler receives the current parameters PS and the choice continuation L and the continuation K. And it can start by doing a step of automatic differentiation that calculates the gradient of L with respect to PS. So we would assume AutoDiff implements automatic differentiations. Of course, in languages with built-in support for automatic differentiations, this would be even simpler. And now that we have calculated the gradients of the function with respect to the parameters, we can update the parameter by performing one step of gradient descent. And we would assume alpha is the learning rate, so we can update the parameters to be PS prime by moving in the opposite direction of their gradients. And once we get PS prime, we can just resume the original computation with PS prime. So in this case, we just handle linear regression once, but of course, in practice, you would actually have a whole training loop, right? You would apply this handler to each of the input data, and if you have a while loop, then it's actually very useful to have those scoping constructs that can delimitate, for example, choices within each iteration. So one iteration, the choice from one iteration does not affect the next iteration. And this is an example where we implemented optimizations as handlers, as smart handlers that make use of the choice continuation. But in this case, there is something that is not very satisfying, which is this magic number for the learning rate, 0.05. So let's consider another example where we do hyperparameters. So basically, those parameters like learning rate is considered hyperparameters because they control how the training algorithm is performed. So instead of just encoding this magic number 0.05 in the handler, what we can do is, because we are in an effect handler system, we can abstracting this operation just to be an effect operation that returns a float value for us. So let's say L rate is just an operation that takes the unit and returns the float. And now we can abstract over the learning rate from the handler by performing L rate and passing the argument unit, and the result is bound to alpha. And we can, of course, recover our previous behavior by basically just implementing a handler for L rate that always returns 0.05, right? And this is basically just a reader handler that whenever you call L rate, it's going to get you the same value. But a more interesting example of handler, and because we are in an effect handler system, we can actually handle the same program using different handlers. And a particular handler, and another thing that we like to note is, in this case, right, we basically just use the continuation K, because this is more or less just a standard effect handlers that does not use the choice continuation, but just resumes the computation with 0.05. And a more interesting handler in this case would be a handler that performs what people call hyperparameter tuning. So that basically means we would resume the loss continuation multiple times, in this case, maybe with 0.03 and 0.05 respectively, and we compare the loss value we get from these two loss continuations. And depending on which one is smaller, we would return the better hyperparameter. And this handler is also interesting because this is a handler that, in contrast to the previous definition, this handler uses only the choice continuation. It's not. It's not interested in resuming the original computation because the point of this handler is to get a better hyperparameter in the end. So it just compares the loss produces on the different hyperparameters and uses one that produces less loss. So as a final example, we would consider two-player games. It's also another a kind of smart handlers we can write. So let's consider Alice and Bob are playing a game, and each of them can make a decision between left and right. Alice performs first, and Bob performs next. And then the loss is just returned by looking up in a loss table. And let's assume this is the loss table we would be using for this example. Of course, Alice and Bob, when playing the game, right, we don't know the strategy each player is going to use. And the playing strategies are also going to be implemented as effect handlers. And let's assume in this case, Alice wants to maximize the loss and Bob wants to minimize the loss. Then this basically corresponds to a mini-max game, right? And if you actually look at the loss table and reason more carefully about what would the result be returned in the end, you can actually follow the operational semantics, and you will see that because Bob wants to minimize the loss, so when Alice performs left, Bob will perform right, and when Alice performs right, Bob will perform left, because Bob wants to minimize the loss among the two choices. On the other hand, Alice wants to maximize the loss. So for the rest of the options, Alice will actually perform left because 3 is larger than 2. So we get a better loss information produced by Alice. So again, this is another example of smart handlers. And one particularly interesting thing about this example is, in this case, these two handlers, they're actually sharing the same loss, right? But they are applying different strategies in what they want to do with loss. So Alice tries to maximize it, and Bob tries to minimize it. And I hope all these different examples, give you a flavor about what we can do with smart handlers and all the different kind of strategies one can implement as effect handlers. So we are slightly running out of time. So there are more things in the work that I did not have time to talk about. For example, we have one more example that is also related to gaming a bit. So it's Nash equilibrium. And we have this example available in the paper. And in the paper, we also prove type safety. So we prove that operational semantics is deterministic, and we prove standard lemmas like progress and preservation. And we also have defined a denotational semantics that we prove to be sound and adequate. So the denotational semantics and operational semantics actually correspond to each other. And additionally, we provide a Haskell implementation of this whole language design, where we define a selection monad and use it to do programming. So all the examples that I demonstrated, they are implemented using the Haskell library. So they are actually all implementable. That shows, what kind of interesting things you can do with the selection monad. So I will probably skip the rest of few technical slides, but you can see more about them in the paper. So there is some reasoning about termination of the calculus. So if you just work with standard effect handlers, actually you can write a non-terminating program. And in our case, we would actually be impose a limitation of this effect system, and under this limitation, we can prove that the calculus is actually terminating. And this is the assumption we had on the effects. It's what we call well-foundedness of effects. And under this assumption, we can establish termination for the calculus. And here are a few slides on the denotational semantics. If we are interested, we have a whole section on that in the paper. So this is the section monad that we actually use in the end. It incorporates what people call interaction trees, or those effect operation trees, where everything is basically a tree that each node is an operation that can be handled by a handler. And in our case, we also needed to take care of the selection monad, and this is where you can see the selection monad comes into play. And there are more definitions, but in the end, we proved that this denotational semantics is sound and adequate. So in the rest of the time, actually in the last just 2 minutes, I will talk a little bit about what we plan to do next for this work. In this talk, I have presented a fairly complicated direct operational semantic for this system, and this is actually how we implemented it. But in practice, maybe what you want is a translation of effect handlers with choice continuations down to just the standard effect handlers, right? And that is useful because now you don't have to change the operational semantics of your language, but you can implement the semantics on top of existing programming languages that support effect handlers. For this work, we did not support effect polymorphism, so every effect epsilon is just a set of concrete labels, but we do not see any fundamental challenges in extending the calculus with effect polymorphism, especially there's a lot of work already in the literature that support effect polymorphism for effect handlers. And our Haskell implementation is more a proof of concept, right? It provides a prototype and which we can program in, and we actually use it to implement all the examples. But if we want to actually do something more serious with it, we are currently trying to have implementation in the JAX programming language, which is a Python library for accelerator-oriented array computation and program transformation. But what's interesting about JAX is basically it's a functional domain-specific language embedded in Python. So it has lots of functional programming flavors, although it's a DSL written in Python. It's somewhat well known in the literature that selection monad itself is not very efficient. So we are trying to incorporate what people do in existing work to improve the efficiency of selection monad. And there is a paper actually pretty recent also this year about a more efficient selection monad encoding. And if you are interested in learning more about this work, so we have this PLDI paper that you can take a look. And Gordon also presented at LAFI last year about work in progress translation of effect handlers with choice continuation down to standard effect handlers. And we also have this extended abstract at ML for Systems at Europe's 2023 that talks about a sketch implementation in JAX. All right, that's all I want to say, and thanks for your attention, and I'm happy to take questions.
All that kind of technical stuff. It seems like the thing is take the parts you're making this choice off this kind of like I assume that like Jax is a pretty good motivated example. They're saying things like, you know, so yeah, you said all of that. I think the shop would work this out there, but in practice, or in user perspective, how does using these techniques in the context of Jax, how does that affect the experience for users?
Yes, that's a very good question. I think I'm asked to repeat this question. So the question is how our design affects the end user's experience, especially in the context of JAX. So you are completely right that JAX and those kind of machine learning programming was a major motivation for this work, where we would like to abstract over all those different optimization algorithms you can do for different machine learning training algorithms. And if you look at how people implement machine learning libraries nowadays, it's quite miserable. Like people repeat, copy and paste the code everywhere and change it slightly just for a slightly different logic, and maybe they apply a slightly different optimization algorithm, and the whole repository is just full of code that is repeated and copy pasted from different places. So the original motivation of this work is, well, if the thing you care the most in a training algorithm is, how to pick parameters and how to pick hyperparameters, and maybe you want to decide which training model you want to use, especially there are lots of different training algorithms, why don't we abstract over all these logics in a more abstract setting, so user can just, write training algorithms without worrying about how those operations will actually get handled. And then maybe you can later plug in different optimization algorithms or handlers for parameters, and hyperparameters just are different handlers, right? And you can apply, you can handle the same training algorithm using different handlers. You can support different effects in a single program, because maybe you want to do state operations as well. You want to do random number generation. You want to do parallelism, and non-determinism maybe, and exceptions. So now you have a very unified framework to do all these kind of things. So this is basically the dream, the word that we dreamed about, right? Of course, we haven't got there. And one particular challenging that we have found during the development of this work, especially through talking to machine learning developers, is they sometimes find the concept of effect handlers overly complicated. Like not even with selection monad, just effect handlers alone. Right, it's difficult to imagine about those control flows, like things get interrupted and then things will work in a different way if your handler works differently, maybe resumes original computation twice, and now the whole stack needs to be captured, and especially if you have multiple references, and how are all these things going to work? Right. So this is still something that is currently working in progress. So we are trying to see, maybe, this programming paradigm is still going to be useful, but what we need is more tools to actually help the developers to understand the underlying semantics better, and to, especially, through development of maybe libraries or tutorials, examples, larger case studies to demonstrate that you can actually do better with this programming.
Hey, Ning.
Hey.
Always great talk. Great work. On slide 49, you made a point about not doing the continuation, and maybe there's a misunderstanding on my side. Could you explain that again?
Sure, if I can find the slide.
So one after that. Yes, here you don't resume K, but we only use the loss continuation twice.
Yes.
How is that?
So the point of hyperparameter tuning is you're basically trying to run the program on a smaller set of data points in order to find better hyperparameters that you would actually use for real training. So here, the point is not that you would like to resume the original computation with the hyperparameter, but as long as you have called the choice continuation using different parameters, you would already produce the loss values. And then you can compare the loss values, and depending on which one is smaller, you just need to return the hyperparameter tuning. And now you get the value of the hyperparameter. You can actually apply it in a different program that would actually do the real training. So in this case, resuming the original computation is not what you want, but what you want as the final result of this whole program is just a good set of hyperparameters.
Yeah, I see. That's why you're aborting the computation.
Exactly. Yeah.
Thanks.
So how baked in is the choice to use reals, the measurement for the losses? In case for the passwords, if you have a tie, you might decide to return the longest one. So maybe you need a pair of reals. Is that?
Yes, very good question. So, I forgot to repeat that one. But this question is about why we use real numbers as the loss, while we might want to use pairs if there are multiple loss values. So that's a very good question. So in the semantics of this work, when we define operational semantics and denotational semantics, it's true we focus on real numbers because we are interested in more first trying to establish the foundation of this language, and later maybe we can extend it with more options. And in the Haskell implementation, actually, the encoding is happy as long as the R is a monoid. As long as different loss operations can be accumulated together. So it's possible in this setting to actually, have pairs of losses, and then maybe you want to do things differently, and especially you want to find, maybe there's no best choice, but you want to find a pair of options that tries to optimize in a certain way, or maybe it's in the end like a weighted sum of different losses. So it's possible in the implementation, but it's not yet possible in the semantics, but we are very interested in doing that in the future.
Great. I'm wondering, I guess, also from the side of what are possible applications for this, and I guess you sort of, well, the terminology used, the application you give, which is clearly this is geared towards machine learning. If you consider so applications for machine learning isn't the primary thing you're using, for instance, within a compiler, you might have some black box optimization, something like that. Have you considered those sort of things? Is that something that your goal, for instance, to make it easier to use like an ML model within a compiler, the other kind of black box optimization?
Right. That's a very good question. So the question is, if you think about compilers, will this programming paradigm maybe be useful as well? I think the answer is potentially yes. And we are very interested in also trying to find more applications of this programming paradigm. We started with machine learning programming because this is how we get into this work. But I could also imagine, like in processes where you have those decision-making processes, or where you would like to potentially apply different optimization algorithms by accumulating loss informations, I think this paradigm can be very useful. And I'm very keen to know more about what kind of compiler optimizations you might have in mind, because we were definitely interested in thinking about more applications for this.
Cool. Perhaps more technical questions. So if you pick and loss, you have a choice loss, and so on, right? And then, for example, in this example, it will globally optimize across all choices, right? But could also the first choice have access to the current loss to apply some heuristics, could store some eagerly?
Can you repeat the question?
Yes. You have a choice and then loss, and then choice and then loss. In the first choice, observe the current loss.
Can the first choice observe the current loss? Yes, it will always receive whatever loss that comes from the rest of the program. So it will receive both losses. And while I believe the second choice would actually only observe the last one, because what happens before you does not matter. It's not what you can affect. And you can affect what happens afterwards. Cool.
Yeah, so I have a question about something I guess would be called time traveling. So it's like when in your picking example, you have a loss after the choice, and it's effectively that all the other unpicking choice. So it's like after you specify the loss, you time to the choice, and you dictate that this choice is picked and the other choice is not. So I was wondering, that would work. The continuation computation is pure. But if the continuation performs some effect that you might not execute, like launching missiles or something like that. So you first explore all the choices, and the effects are already performed, and then you make a choice. It might be too late. So is that a problem that can be solved?
Very good question. So the question is, what if the rest of the continuation performs some effect, and then the choice continuation would have already performed those effects, which can be undesirable for the user? So this is a real problem, I would say also, or a feature of this system, which is the rest of the computation will be wrong in order to calculate the loss. And it is ran for a good reason, right? Because maybe your loss value actually depends on what kind of side effects you want to perform, right? Maybe you have to read from a file to get some value in order to calculate the loss. And maybe you want to ask for the user for some input in order to calculate the loss. So if the loss actually depends on all those side effects, then those side effects have to happen in order to calculate the loss. But it's true that maybe sometimes it's not, this is not what you desire, right? If in fact that prints to a string, right? And now the user writes a handler to handle this program, and suddenly we print twice to the string, or print multiple times to the string. And this is also an active direction that we are currently trying to explore, which is how to design the semantics so that it better fits users' intuition. Right, like if you ask the user for some input, maybe when it resumes the computation, you should be used the same input, right? It makes no sense for getting one input to calculate the loss and then ask for a completely different input that will actually produce a different loss. And another way to maybe to make it work nicely is to limit the loss continuation to be a pure computation. Like we can actually analyze the loss continuation and analyze the data dependencies of it, and maybe you would have a strict requirement that this loss continuation must be pure in the sense that the final loss value you would get does not depend on any effect operation. Then you can just strip off all those effect operations and get a pure loss continuation in the end. So these are the possibilities that we are currently considering, but you are definitely right that in the current semantics, maybe this is not what you want, and this is, I think, currently also like an open problem we are actively trying to solve.
Any other question? Okay, so let's speak again. Actually, we're suffering.
Yeah, I know there's. Oh, yeah. Yeah, I mean.
You don't remember? Yes, yeah, I do recall this. Yeah.
Like, I missed that.
Yeah, I saw it in the flash. Yeah. I said he was should be there. People crazy. Not there.
It was.
No.
No.
Okay, if you just well, maybe look, he was eating his bowl of grain
I don't think that's like.
as usual. His Tupperware of grain. Yeah.
Not in the function, not in like this is a function you go, like you go out, out. How about you? You go. You can't, even if you like know, like you still have to like exhaustively like map that thing, like to like just call yourself, get a value. It's not sufficient to just recursively call yourself, you know how to pass that.
Ja, ist genau das, was.
That record can never happen. So we should just do something more. Ja. Aber ich spiele
Yeah.
Where's the unbox?
No.
Well, I mean, how much will draw?
But if those single.
Yeah. No, that's not. No, this is like.
So this fucking didn't say.
Once you fix this, like X is gonna be sad, like this thing doesn't do it. Like it just doesn't do anything about them. Functions like. Yes, right. Like.
Yeah, but that part's the part that changed.
That is going to be very useful.
Yes. Yeah,
I think the only thing that is just.
That's why I was I think so. I think they did very well. Let's see.
I know partial is like
We talked about this.
going wrong between us. It wasn't that.
It was not that.
Right, and that's-
Now.
I
like direction agree.
Because, and then
That's
as
right.
in
The problem with that
solutions.
Yeah, they're completely.
Along with
That's
that.
the paper fight, but I didn't, what they're doing.
Right, it's like, it's hard, like you're trying to do this stuff.
All over.
Recover a static program.
Yeah, no, it's insane.
And also,
you need to mix stuff again.
Sorry, but, like,
Should be.
You only need it for like the top level
Dynamic
record,
programming.
like which like definitely like
you really, in practice.
unless you want to make major changes to the way that like the export.
No, sorry, the top of the record is already fine. It's the subfield that has.
No, but you only array on the size of the top level record. Top level unbound record. Yeah, which definitely is flexible. Like the only way that like
Also, sorry, I meant that the library might be so fun. I think that was I think that was integrated into the information. But yeah, it just has certain dress features.
I'm gonna I felt
Yes.
Another totally
An area
different living room house.
Yeah.
Seems like you're always living the dream.
Average for us, this is like not.
Yeah.
Are you ready for this?
Because I think. Because a couple of things, like we have.
Well, according to the official version, or she mentioned on the team, there's also like in
Right, non.
actually,
And also it has.
it's not, it's saying that's not that.
Yeah, so it's.
Because you have a little bit.
It's also because there is a lot of the work I was telling you, but like I guess. But music to go on for the season, we're trying to slow down the stage.
is not really where
Exactly.
Although,
Exactly.
watching the on this was about how to connect to the portal and that.
It was like very.
Yeah, I was feeling like.
And also, there should be a target way to send something to the scripture.
Oh, you're.
It is predictable.
It's not.
Well, I think this was a sense.
I'm gonna say.
It's so.
I'm gonna say.
That posture.
That's a lot. For this sense, let's track back.
Yeah, I think we
I
have
just very recently.
I think we have, we are actually.
Did you also?
I'm gonna go and search.
哦，网友
I was hoping
你好，
that
你好，
they-
哦，你在要如啊，对对对，
刚打的，我看着你的背影，我还以为你是他。哦，有点像是吧？你们今天都穿蓝色的，然后是偷。你看没有？现在去哪？刚来在那儿。
That is very
我去找他问问我，talk slide 发给他，你是在哪个女娲口14号？女娲口的全称ownership 哦 capabilities 什么那些。但是前面
Oh wait.
那个，他现在在公司第一次纠后干。没有听谚语，在咒语。他在当博士后对吧？对，博士后。你们是什么？就是怎么认识？哦，好问题。最早我见他是 R Plus， 我参加了 SRC， 他是苹果的。然后那后来认识，其实是因为我之前本来在日本过去交换留学。然后那一年，我的同期现在助教跟关山一直有很好，叫他就是同期同学啊，对，直接叫同学就行了。对，然后他给我介绍了一下关山。你要跟他打个招呼。
Tables are different thing like this is just wrong. And also
You don't have to get
that's
and then you just do a moment
But it's seminar. That is okay, I trust you. There is a door to that. You have to go or escape.
But you can just find it for certain items.
Technically, there's no doors in between that area and the other. Correct. But these rooms are separated by having that room.
That's why.
See, this is a reasonable temperature.
you still do like there's like if you don't just go that way, it's like some rhetorics.
Sorry, I didn't even.
That's what we're saying. Yes, I agree.
Right?
Yeah.
Everyone's open is to yeah.
Whatever. Or you're getting.
Too.
Yeah. Technically, but like I don't have color.
I agree.
For my hands works.
One nice advantage you get doing the whole graphical thing.
My friends at weddings.
Actually,
The bride reminds me a lot of you. It's like, why? They were like, she cries a lot. I likes Disney. No, it's my two qualities.
That's an art. Sorry, this is a friend.
Wait,
Yeah.
okay.
Friends like this.
If you like a well, mine is pretty great story. It's just that they fine. And like use not a sub program which is
They already have.
Yeah, exactly.
It's like this is how she does.
The hook desk.
And then you already have like a Python library, but Python for constructing that.
Oh. Microsoft is between natural numbers from an exponential. Really?
A huge part.
The natural numbers.
It's hugely valued part of our.
It is the natural numbers that you get
In part of our treatment.
them as a co-inductive.
Oh, we actually, we also like love.
I haven't figured out how.
But like, we lost.
So maybe I would just have a maximal fixed point of text.
Without being that like the data that's.
Giving. College. Just rough.
I'm like shocked there's not more than.
But actually.
I think it's there, it's just not.
Right? Feels like there should be more.
And
Must be like
building.
That's the attention desk.
Building.
it must just be the people who just know how to build. The paint is such to hear. It's like what is that?
You go to our groups. So.
It doesn't look like.
A lot of that is. Most of the.
How is it really tempered?
Frontier models. But there's definitely, I was thinking about it.
You'll say, you didn't think of how the fact that we got here at night? No. Yeah, just like today, I mean, how was it? Not much. Yeah. It's really funny. No, but I'm so hungry.
It's like an hour before.
Whereas the. Your age going off.
That's one thing I like.
It's hard to.
So, like, leaving them very
Trying to find, by the time you get a fine tune.
that I would say.
You want to have.
Then you don't even.
And so that's a better. But neither is Leah. Okay, so there's two of us. Yeah.
You give me a talk about condition, you do some.
So. We're just gonna pass.
But there's like.
No, it's just, no, it's not a pass, it's just expected.
How do you get the right control?
It's like, you don't expect, we expect no better than
Privilege. Yeah, exactly. Agreed. I should get a fun name for mine. Yeah, to put a name to it. Can you do that? Point? There is a name for it. It's true.
Yeah.
Yours?
And.
No, there's like an actual name for someone who doesn't like food textures. Oh, sure. But anyways, I assume one will be sandwiches, and I don't eat sandwiches.
You don't need sandwiches.
If you want to be like, oh, please.
You're
You're a law.
See?
not sound very
Depends on what the ingredients are. If it's like a hamburger, it's fun, I eat the burger.
It was like.
It was a texture question.
Just the dog,
Oh, so not in the bun.
not in the bun.
Drive how you time line.
Yeah, it was a texture question.
The agenda.
Just the dog part.
But yeah, like ML is a huge.
We saw this, the cutest dog.
Yeah, that's true.
See,
The cutest
And so I think it's nice that you double the flip when you go away. So then
That's so cute. So cute. Actually, it's kind of cute. Now that I'm looking at it for a little bit longer, it's just looking for food. What is the name of it?
According to Siri, it's an honor.
So very good question. I have this action next year. It's I just need to go through this whole
That sounds
We're in Asia.
order to make it happen.
Near the water.
And I'm just still hesitant.
It's like
to
right
ask
close.
you the stuff
That does look extremely
because
familiar.
it's-
Yeah, I love how it's.
But I should do it. So I would give it. I'll have to start maybe-
Oh, yeah, that's, yeah, that is. But number two is like, I don't really care if I read paper.
It's a specific paper I was thinking about, where it's just makes system is easy now. Yeah, constantly so integrate. But I don't. Yes, but I don't know enough about the area to say whether this is a fiction, this is also shown in the bugger. But I came up with something that maybe is basically nice to with games. Maybe there's a way to take advantage and sort of implementations on the search strategy itself, like for instance. You can tell that like a certain.
Is it blind?
Or like this path is definitely not going to be better than a path you've already found.
I mean, it's like a snake,
But
probably like
something
5
that's
times.
else is this? Because I'm not sure that's what you were saying about. There was a question about whether you tend to see the loss so far or something like that. I think that might be important to this.
First, I thought they were squirrel. Oh, yeah.
I think that will also require
First I thought they were
some subsequent of this city.
Like,
which
oh, it's a
I think
squirrel.
is
What?
serial language.
Let's do something.
Right. I think that's.
Means if I'm here, then I can submit weekday work, weekend work.
We were talking about that yesterday. Does that count?
Ellen said.
Oh, nails by manager, so yes. Nice. Nails manager. Very easy. See that for
No matter what future you see.
Harold is also.
Here it is.
Well, that was crazy.
It's also useful to I think receiving a partial piece of this.
But now I feel like. Oh, it's in the
Elbows, man. He
I think that would be really useful. Because it also like
I'm-
this is improving and also
I'm good.
it feels like just fixes on the bad thing.
Yes.
I think there's a negotiation. But I think maybe just like make sure
I'm gonna be going to tidy up.
and then they'll give more guarantees for instance to say
TYE.
Yeah, you have three
You're not
different
using. Oh,
populations.
this is actually different.
Because right now,
What is it?
All the ones that want to go are TYE.
you have sort of.
But on the right side and the high ones.
I guess you don't have to,
Like that's
I
tutorial.
guess you can generate process based on
Yeah.
process.
Oh.
Unfortunately, I forgot all of TYE is in that.
So how do you see like that?
Wait, what are you, where are you? No, it's okay, that's not.
Yes.
So, I mentioned, oh, progress. Yeah, guys, if you haven't started anything. And then you can go to filters. Oh, no, you're good, you're good, you're good. No, click filters.
Yeah, so safety violation is the easier.
Seeing for starting things.
Violation, liveness violation is all of the other lists.
Keeps logging me out.
So safety is when you have a peer.
Oh, by the way, if you start things the day before, you can download a calendar for it and put it to your account.
So these are, this is classification, which is under the.
It keeps logging you out and I think I'll just follow people around. That's
Oh, my.
That's my plan for the whole week.
Well, yeah, I mean,
Yes,
some maybe I also need to conjunct what the condition that you want.
Yeah, exactly.
Honestly.
Yeah, that's also this is not the reason why it is violated.
Yeah.
Yeah. Cool.
Like this work like this is a new legislation.
Actually, your liveness violation is not a safety violation.
Yeah, oh,
It's
like
it's violation.
People who are having it. Who are like, oh, you can run those this last day. Yeah. Not speaking.
Yeah.
I was actually sorry because how would you convince them to use
Sorry.
this better than, well, for instance, with facts, I think it's not efficient, like, can just have. Measure certain and maybe, well, this is.
This must be something more than that.
If you know.
Because
that's like just like an undergraduate.
There's a lot of different searches happening
Wait,
with
like,
the same program.
encoding?
You can see a lot of the.
Like,
benefits.
this is gonna type theory.
Like,
It's also remote.
Here's a higher.
Okay, let me think one additional That's also on
research hyperparameters.
Also, I don't really care. Sorry, this is the only one that I want to
Obviously,
see
with
today.
the style, we don't have.
The one that couldn't to are going to something
Is something that
is the third part.
Becomes so which is not displaying, which is.
Exponential communication.
But this is also something that we have to consider and go on and think about. I think the
Because
so that actually right.
this is an area that my professor did not get into very much. That was very applicable to the fact that it's used for verifying for encoded carbon. Yeah, it's really interesting. It's for handling non-terminal processes. Yeah.
Most of the time, if I program.
Yes, that is the point, is that if you just use.
But I'm also thinking, I think.
And you have to things to represent it, and it's fine.
Very nice.
Guarded, so languages like ACTA and Lean, I think probably require some kind of facility that they can.
Still static.
Also,
That's
yeah,
all
one
true.
of you this Python, like the main project to develop on this. I feel like it shows like all these things you should think about.
The guarded just says like there's some variant that you have
But they
to
don't
follow.
know, that's just the.
So it might be like, that's some variant for some property that
Yeah, just like, oh, it's all the evolution of.
Instead of just actually. So sometimes the phrases stay the same. So. Yeah.
But the coolest parts I've seen is ours.
So it's hard to explain this point without demonstrating what is the
Trace the execution of a function in Python. So you can, for instance, by the way, if you have an if statement, then the value that appears in the condition has to be a boolean, like magically where it makes have a decide, like a choice set. In order to be executed, which I think in this case would be great. If you could do that in Python, then the sort of capability to do tracing there would be really interesting. So maybe I'm missing something, but I think it's very interesting.
So,
Yeah, something interesting to clarify.
I have a chocolate.
I assume they're all like.
I have two, so you're gonna take one and I'll take mine.
The only negative. This is a violation. We don't know why.
I said they're probably all custard.
Let's, yeah.
Like, they didn't look like they're just full, like, consistent dough throughout everything.
Perspective.
I take a detour to the
More clear.
McDonald's. 6 minute drive.
Right. Give a card?
No, I'm just gonna go on that date. It took us 2 minutes to find the taxi.
Why they are called like this.
10 minutes for the fucking text to show the logo.
Really?
For our text.
What app did you use?
Because it needs us to.
Or it literally got like 2 minutes. Yeah.
So our friends are
We did an Irish goodbye, right? So was it a big deal? I really was stressed when we got here. I just like, yeah, there goes. No.
I got the,
Here's the ramp, there's the ramp.
I got the vibe.
Oh, yes, because this is the different matrices, right, that set off it as people use implemented and research. And they called it smart choices, and then we decided to call it smart analysis.
So is this work?
I think it's Google research, so it's mostly a set of data internally. They use it for a lot of things, internally. I don't know if they actually, but they do have a big like this, Well, I think the example I like is they talk about caching, where you would like you read from memories, right? Sometimes you want to cache your responsible. And they talk about what kind of strategies you can use to model this caching.
I think that's exactly what I feel. Like, that might exactly be like.
That's you, the same as
Like you get like a way to have this within the unified pyramid, like others. Which I think is something I'm trying to get with Pythonders, that a lot of the work seems to be around how do we express this specific thing as a general thing that I guess is now getting popular, which is a Pythonders, I guess. That's my, would you agree that this is the case with all of the Pythonders research? Or is there something that you get for being an attacker? Community cards, just express it.
Right. I think this is a very good question, and to me there are always two things to do. The first is modularity, and the second is the ability. I think maybe sometimes modularity is more important because now we actually structure the code better. Handles and maybe handles it's handled in different ways than the model does. And uniform framework is also nice because you would expect things to interact very nicely. And sometimes they don't if everything is right? There's still modularity, but implementing is different. But that's what they don't interact.
Well, that's a good point. Yeah. Unifying frameworks are modularity.
Yes.
Cool. No, that's a really interesting point. Yeah. Cool. I should give you a break, but I wanted to catch you later about parallel algebraic Pythonders. Since that's a paper you did last year, also as a people I actually looked at it recently. I want to give you a break after the short. Yes, cool. So thank you for the time.
Flowers. So the previous intention is that this is isn't its usage its usage. Like the other one I did it in the backup sites. So this one is invalid in discarding of resources because it never returned. In one case is unused, the other case is used. I think we don't have enough time to discuss in this study, so I.
没有什么，就是如果你不是空的话，你会有一个这个 value 一个测试。对，
Intuitive explanation is that using the desired code operator.
就是比如说那个
I mean, here I want to say that
tax systems are good in variant-based reasoning. And resource solution can be established using type safety. And usually states, and then this supports type state systems and linear type systems and provide support other type state systems. It's more resource usage analysis.
那种是的，然后你把它去掉了，可是我觉得这种算
Yeah, I'm not sure. Yeah, and these two bullet points are used to explain what their technique is. So they usually apply something. And then say what that says on the I don't have any citation for that. I don't find suitable word. Yeah. So.
学生丰富发现，就是我是太好了，你别别。
Versus on session types, but I don't think that's very relevant.
There's a main motivation.
Yeah,
你可以把它那个到。对，差不多。但它只是因为去年9月才上，后的时候它才开始死。对对，就其实就开始发火了。因为基本一看那个，你看猜了。
Very curious. I don't have
对啊。
viewers.
Oh, the
Because I think the why this is hard because the technique on this requires reading about and then we try to explain it using more examples. Then our goal is that want to have systems and restate that liveness is about produce not just valid prefixes but also valid full usage traces in the execution.
你要看那个钱，太贵。我当时感觉是在通货上搜的，就是黑的那种的，就是最你太过了价值币。我是走哪块儿是那个什么？是杀出来的。
This topic is about to be over soon. Probably won't get some tea or whatever anything because
Should I?
Yes. Yeah. No, I've been told like some of my students might hear that. So yes. No, hi Emily. Yes, yeah.
And these the programs are always funded by contributions.
对，而且他们这酒店服务员不为了让他们，我说的那个龙沙那个，就给他们我们酒店上面的学费本身沙不是在网上写的，就是有一篇那有一个写的是新的网上，那括号里写着吗？ Okay,
so that's a big okay. Okay. Part, and I think the first part is about problem definition. We have used some examples to intuitively say what we are, and then this is our focus. in this talk about the progressive linearism, and then the third and the fourth part are not covered, but I say that there's another potential violation of Leibniz and also science is to not use traditional type safety, but we usually rely on the progressive nature of and these are all about the first part, so I think it's more intuitive. Something working to make using these three all these from the set of doing all this stuff. And realize that we get this bias here. These are certain rules that you in this case you look to brush of types and this is taking rules of long languages and people just know the long. Let's raise the bias definition again. Here and I would stay here. All the same things, of course. That's use it as a tiny. I got this like this is something like say in a very small niche. Maybe I should remove that. Oh, okay. So it's just that this is a valid thing to represent here I also want to explain that yes, actually these are standard rules, but I can introduce the notion of evolving states of the resource. And I want to explain that the sequence of visited state of the actually represents the evolution of the species. Not something you can say. And then this first part is about model effects and there's we need to track the states from types. Examples, all the text states, syntax, CC, and bioinformatics stage, so that there will be some examples in here. Yeah, so this is something because here we say that when I was looking at the surveys, hello, I'm Richard. So I just used the yes. I checked that it should work, but I don't know how this. So that
okay, so maybe you can
no,
That's a better take for the just to
share that you are quick.
Sometimes it's too far from my program.
you have the zooming on the.
I have this in the comment for that. I would like and when you do that, then you feel so much more about it. And I think the character actually has that.
This is
It is how it really works. This is all of the video. Typically, of means that is to value on too much abstraction. There is a problem. I have a problem, but I haven't really. It says I couldn't use it from ICFP. Oh, now I can from my HES address. If you use from that is work.
Just share the.
Yeah, it's nice. I mean, I don't want something that. Yes, so and the entire so I'm not anything the yeah. And yeah,
Yeah, it works.
Is that something you do?
Okay, so I try to watch.
Yeah, just so that I don't have to work on it.
I read the question.
Yeah.
Yeah.
It's worse than
I guess that's okay.
Yeah. Yeah.
If you have a euro, you don't have a euro, I guess.
no. That's structured.
Provide the phone number, US number, so I put it down.
Okay.
So is there a code for?
Let me look at the,
Yeah.
Yeah, because put the Bible, I think.
Is that your bag? Okay.
Yeah.
I got a local symptom, whereas, when I arrived with broken for sure.
Yeah, I was looking at it.
And then I'll give you this. Hello?
Okay, great.
It's a test.
Yeah.
Okay, so, this is transition for complete. So maybe, okay, so this is not a system. The function is provided on planning and about some executive functions that in the computer.
Yes, thank you. And just to say, this work is really it's kind of work in progress, but we'll see as we go along that it builds on some techniques that were kind of developed quite a few years ago. I wouldn't say maybe 30, 25 years ago. So let's get started. And the whole idea here is to get towards some kind of effective memory management, and effective in the sense that it should be a little bit easy for the programmer to specify and control memory effects. So there's been a lot of work on reasoning about effects in higher order programs, effect handlers and whatnot, and type and effect systems that this work is built on. And some of the questions you ask is, of course, does a program make good use of memory? And maybe parallel threads, do they execute without allocation? mutation races. Are there unhandled exceptions? Can a function mutate shared resources? All of these things, and there have been developed many solutions to solving some of these problems. But the goal here is to provide some predictable behavior and control with only few programmer annotations in the program, and it should also be scaling. That's some of the goals, that we should have some modular scaling facilities that you can actually deal with large programs and deal with rich set of data types and functional capabilities. So I will just say a little bit about region-based memory management and region inference. So you guys can see also here. There's this idea of explicit region-based memory management, where the programmer will associate the lifetimes of objects with the regions, and then reason about how and so on these regions are allocated and deallocated. And examples are, of course, Cyclone and Rust. And then there's this notion of region inference, which in principle just takes a non-annotated program, and then it will do its best to annotate the program inside an internal representation, and then it will use those annotations, and hopefully it will find a sound way of annotating the program, so that a backend can really generate code that will use regions as the underlying memory management strategy. So here we have the traditional work on regions, where you have a stack of regions. So the stack can grow, but each region can also grow independently of the other regions while the program executes. This machinery then has been incorporated in a compiler for standard ML. I'll come back to that. And then REML is this language built on top of standard ML, which will allow the programmer to make some annotations. But it's also the case that an ordinary standard ML program is also a REML program. So you can kind of start with very few annotations or no annotations at all. Everything will be based on region inference. And then the idea is that you can start having the programmer annotate and then control and get guarantees about memory. So we have this notion, we call it gradual support, even though there's no kind of runtime things going on here. So the gradual part is mostly that you can you can basically choose where you put your annotations, and then the inference will do its best, and the inference will also, the annotations will be respected by the underlying type system. So for expressions, for instance, you can say that you're allocating a pair 4 and 5 in the region R. So you have this backping annotation there with the regions. And you may also annotate types with regions, where you basically, there's another way of saying that the pair 4, 5 should reside in region R by specifying a type, a region annotated type that basically says that kind of constrain the value to be stored exactly in that region R. And then you have this effect scoping, where you allow, and we use width as the keyword here instead of regions. But width is a keyword in standard ML, so it was a trick to kind of get a new way of actually having backwards compatibility. So we can have these width declarations where you basically specify a region, and that specifies the scope for that region. And then you can also define functions that take regions as parameters, and so on. Function declarations may also be annotated with these contractual effect constraints, which may be used to say things like that two sets of effects should be disjoint. That might be a good thing for executing two different expressions in parallel, and then you know that there will be no allocation races between the two functions when executed in parallel. And this REML then is built on top of the ML kit, which is a compiler that has been implementing with primarily just with region and effect inference. So the new thing in REML here is that you can provide these user annotations.
So is the width actually allocating a region, or is it declaring a region variable?
It's basically lots of analysis going on, which might define that this region, there will only ever be one value being stored into it, so it's allocated on the stack. So there will be space on the stack to be.
It's a hint to your existing region inference algorithm.
It's a hint, but it's also a contractual constraint, so to speak, that if some value is not respecting that scope,
right,
then you get an error.
Right. Yeah. So it means there has to be some region.
So there has to be some region that, and you might use that R in some allocation specification and so on. And if the region type system will not be satisfied, then you get them.
Yeah.
So let's just go back a little bit with the region inference stuff. I'm sorry for giving you a little bit of background before I get into the new stuff, but region inference is really this idea that you take a source language, the lambda calculus with letreg expressions, and then you have these possible annotations as explained here with row and end, and you can every allocating expression is then also annotated with the region in which this value should be stored. And you then have these inference systems that will allow you to generate a new expression E prime, and is a type and effect system, so it will also carry an effect, and you have an enriched type system, a system of types, where types also have effects on the arrows. So here's a simple example of the region inference in action, where the inference algorithm has figured out that there are some local regions, row 1 and row 2, and then there are some then there's a more global region row here, which will survive the execution of the program and store the value of y. So here we have a local pair being created in row 2. We also have a value here, which is created in row 1. Then we project the second component here, which is this real in here. And then the two regions allocated, row 1 and row 2, they will go out of scope, being deallocated, and then only row is surviving, and the value in row. So that means that the region inference can maintain this idea of having local memory, and it will be type safe and so on. There are lots of issues here, and with higher order functions and things like that, you can get so-called dangling pointers that will refer to some values which will never be used in the remainder of the computation, but it can be shown that they will never be accessed, and that means that region inference can actually get rid of that memory, even though a tracing garbage collector will not be able to deallocate those things.
Martin, if you had one of these grid blocks, if you return the closure actually some data that's stored in that region, that would be a type error.
There will be a type error, but only if that effect in that closure will be executed at some point later on, right? So if the closure is not called for some reason, the effect will not appear, and then you might actually have leaking closures can be fine, but it has to be a little bit more. They have to appear as free variable in another closure to see that example, because otherwise they will appear in the type of the closure you are returning, and then and then you will basically not be deallocated. So you can get some advanced cases where you will have these dangling pointers. So here's some support in REML where you can be explicit here. Example, again, you allocate something, you project, and you also have a notion of global regions where you're allocating something in a global region and you don't have a width construct. So you have some kind of built-in global regions that you can use for various cases. And of course, a sound annotation of your program will just be to store everything in global regions and have no width constructs at all. And that's actually also a sound way of region inference. That can be the choices it does, because that's would not be good choices, because then everything will just live without being garbage collected. So region inference is about finding a best program, so to speak, that somehow will deallocate as much as possible during execution. Yeah, that's because, and why is it called R0 pair? That's because the underlying mechanism here is doing a lot of things to try to get untagged and untagged representation of pairs, for instance, where the pairs are really just stored as two words, not with a tag header and so on. And that means that the R0 pair is a region in which that tag is stored with the region and not with the values themselves. So that means that there are some specifics, and this is one of the things that we would like to kind of get away. This is actually a good question, because this is really, for the programmer, this is not too nice, of course, to be able to have to specify it like this. But until now, we have been kind of limited that we have to respect the underlying implementation of how pairs are implemented and so on to deal with this. But this is actually one of the key points here is that in this talk that we would like to have a more abstract notion of what a region is than just the specific ones that are implemented for the sake of performance and so on. But you need to wait for the programmer to actually have the possibility of working in a more abstract way. So here's some examples of a function that will take a region as an argument and then will return a list in that region. And here we see that the list type constructor is an integer list, and then that list is stored in region R. In fact, the pairs that makes up the lists, they will be stored in the region R. And then we can call the function, and we can kind of extract the first element and then again deallocate the list. Here's an example of a so-called called a region exomorphic function, one that will take an argument in one region and then it will possibly return a value in another region. It might return a value in the same region. That depends on the call side and how the function is instantiated. But it does allow for the call side to specify two different regions for the parameter and the result. And that's a copy function here. And of course, if we're not copying the tail of the list, then of course the type inference system will enforce that the two values that the returned value will be stored in the same region as the argument. And if we don't, if we forget to put the copy there, then the implementation, the type system will complain with a type error that you cannot unify these two explicit region variables. So this is one of the features that you gain from programming with the system. Here's another example of something called an endomorphic function that will really return a value which is stored in the same region as one of the arguments and not in a fresh region, so to speak. So here we see that we are appending. This is the usual append function, and that will of course share the the right argument and cons all the left argument elements onto that onto the second one and return that new thing. But that will be, since we are now having sharing between ys and the result of the function, then that those two things will have to live in the same region. Of course, we can explicitly copy ys first and then call append, and then we can write our own thing that will really deeply copy the entire list instead, and then turning that one into an exomorphic function instead. Okay, so so how do we actually program in the large with such a system? So we saw some very small examples. It has been used to enforce these things, as I talked about, mentioned earlier, the notion that the effects of two functions should be disjoint. That will allow for for reasoning about absence of allocation races, and this notion of effect constraints can be used for these things that are built in. I'm not going to talk more about effect constraints here. And then there are also examples. Region inference support this notion of polymorphic recursion in regions, not in the types, but in regions that allow different call sites within a recursive function to use local regions for those local calls. And that will allow for instance, things like a merge sort to behave efficiently and deallocate the temporary sorted lists, for instance, and deallocate those after you have performed the merge operation in a merge sort. But it's very fine-grained, as we also saw. We needed to annotate precisely what regions things are allocated into. How do we actually allow for programming with some larger structures? So this idea that we will introduce here comes all the way back from this paper. And that was in the FEST script for Robin Milner. It's from Lars Birkedal and Mads Tofte wrote this paper on contractions, which is basically defining the fundamental toolbox for defining unifiers for types in terms of substitutions. So with these effect sets. So the problem is that once you start having effect sets in types, effect sets on the arrows and types, what would be a unifier for unifying two types with such effect sets locally inside? How do we actually find a substitution that will make them equal? This is a notion of contractions that they came up with, and really you're then trying to unify these effect graphs. And there's a kind of a mathematical definition of all these things under what circumstances they are well defined. And this also goes a little bit into the notion of region inference itself, the termination proof that the inference will terminate. And that termination is based on the idea that first you will create a lot of fresh region and effect variables and spread them all over the program. And then you'll start you kind of want to make sure that the typing rules are satisfied. Also, in particular for the end resulting expressions, that the typing rule can be satisfied. And various places in the typing rules, you will have to unify. In function applications, for instance, you need to unify types. It's really Milner's algorithm W that comes into play here. So you have these unifiers. And these are the contractions. So after you have spread fresh region and effects all over the place, you start contract the program and all the regions and effects in there, and you still get something that looks like effects. So that's a whole theory that they developed there, the notion of contractions, that are these substitutions that will make sure that at the end you can only contract, only making things smaller, and at the end you have in the very worst case, you will have just one region, the global region. And the program will just use that one region in the worst case. But of course, it will try to do something better than that. And there's a notion of principality in unifiers and so on, that you can find the best contraction that will unify these two types. And now the idea here is then that we can try to use these contractions to make programmers specify more, so to speak, high-level types for functions. So here's an example of a compiler, and this is where it's work in progress. So this is not fully implemented. There's some way to it, and there's also some work on actually defining the underlying properties that we will need. But let's look at an example of where such a thing could be very very nice thing to have. We're assuming a larger program here, trying to write a small compiler for a functional language, and we have some compilation passes. The first one will parse and type check a file, and then we'll return some AST data structure, abstract syntax tree, in some region R. Of course, underneath it will really be in many regions. This data type will usually, after region inference has played its trick, it will be maybe in 8 or 20 regions, depending on the size of the language. So what we want to specify here is that there's just one region. We'll just call it R, and the AST is residing in that one. And also there should also be some compiler from AST to IR that will take an AST value, and then it's exomorphic. It will return a new thing and a new internal representation, IR, and store that in region R2. And notice that we have this idea that R1 and R2 should be disjoint, in the sense that if you can write the function like this, you can pass in and specify that R1 and R2 are the same, but you can also call it in a context where they are really different. So you know it's exomorphic, this one. Optimize, on the other hand, will try to take some IR representation, will do its best to optimize it, but it might also just return, just be the identity function, or in some cases it can't do anymore. It will just return the argument. Then there's a compiler from an internal representation to assembler again. We are here assuming this is exomorphic. And that can be checked that this function indeed has that type. And we can then finally emit the thing, the code here. So let's then see how it's usually you would write the compiler function from start to finish here. You have a compiler will take a file input and a file output, and then it will parse and type the file, and it will compile it into an AST. It will return an IR, and then it will optimize the IR, and then it will generate assembler code and then emit it. Now, region inference will do good on this stuff, but it will not have the optimal memory behavior as you could if you kind of allowed for a little bit of lead floating in your program. So you can rewrite the program so that the AST is not alive after it has been compiled into an AST. Right, the memory that will be set aside for the AST can be thrown away once we have the IR value. And this is what the program to the right. Here we have done the lead floating, and then we have also specified explicitly the regions into which the different into which the different ASTs and IR values will be stored. But we're not being explicit only at these kind of virtual regions and not at the specific ones. And this will have a much improved memory behavior, of course, compared to the original. The problem here is this thing with that in reality there will be many more regions, and we need to find a way to kind of allow many regions to kind of be allocated in one virtual region. And this is where this notion of contraction comes in, because these contractions kind of can make can kind of map each of the regions into a particular one region. So for instance, the AST, if it has kind of 3 local tuples in the AST, they will be allocated in different regions, R1, R2, or 3. But with these contractions, we can kind of make them look like they are allocated only in one region. And that means that we can have this annotation ASTR that will basically just say that the same region here, or maybe the same region of different kinds. We have the pair regions that are specific and so on, but they can actually be grouped together so that we have a much simpler system to work with from the programmer's perspective.
So this regionality is inferred by the compiler, or is it the user that is very?
It's inferred by the compiler, and what it does is it looks at a data type definition, and then it will basically see there's a constructor that takes a tuple with 5 elements, there's one that takes one with 3 elements, there's one that takes 2 closures, and so on. So it will try to define the arity, and that means that the auxiliary regions in which a value of that data type is stored is basically given explicitly. So you can imagine then that if you have a full program, there will be a lot of regions around to read, this is this and this is that, and so on. But of course, from a programmer's perspective, you really want to collapse those things into one chunk of values and reason about it at that level, unless you need to go deeper. So you want to be flexible with respect to that.
Follow up on that. It's just basically on that. This sort of region where it's a different layer. Some sort of like within one of these does not argument this case.
Yeah, that could definitely be the case that they are set aside, allocated. Usually you can also collapse them somehow, but they will be set aside, and not if it's not used, then it will just be an empty region.
Okay, like I'm like
yeah. So just to end up here, we are looking at this. We have all these things with the consistency of region and effect annotations. We're still doing this, and this is ongoing work with the leading contraction after checking is memory safe. And the idea there is that once you have the user annotations, the type system will be satisfied also with these contracted regions. We would like a proof that you can actually not implement it like that. We would actually like to just throw away all the contractions and then use the underlying regions that were inferred for the back end of the compiler, because that will be much more efficient and maybe even better. There are examples where you could have better memory management than being with the explicit one, but we still need a proof for that if you have a contracted system, a contracted program, then when throwing away the contraction, still having a region annotated program, that program will work as efficiently as the contracted one. So this is some ongoing work, and it will require some small steps, store-based semantics, to have a relation between the contracted and non-contracted setting, and be able to talk about what it consumes the most memory. And it also needs to be small steps, since we need to have it maintained all throughout.
Martin, what do you mean by efficient?
And efficient in the sense that we are not allocating more memory in one case than the other.
So your design is based on trying to minimize the amount of memory allocation.
At least making sure that you're not kind of drastically increasing the amount of memory used.
Someone who likes automatic memory management, like one of the key things of automatic management is that sometimes throw memory at the program to make it go faster. Like what was the story here for doing something like that?
That's a good point, and maybe that could lead to 2 different kind of annotations. If you're really in that situation, maybe you want to kind of enforce something. But also from here, we are just from a semantics point of view, or is it really sound to just throw it away? Yeah, this is the first thing, and I think there could be, of course, more ad hoc choices where does it make sense or not, and so on. But is it really sound just to throw it away? That's kind of the open questions that we're trying to answer. Yes, mostly here we are concerned about control. Yeah. Making sure that if somebody else does an update to the program, you still have the things that you typed in. I mean, you still have the properties, right? We're reading inference, you have to analyze the intermediate expressions again. Does it behave as I did last time? Somebody did some change to some function, forgot a copy somewhere, and suddenly the whole execution will explode in memory. Here we can be explicit and make sure that that invariant.
Something I guess. Oh, I think you were originally thought I was just. I did it. If I have to be the same age, I remember that.
There are different in some aspects of readings that are dynamic, that are more kind of, I don't know if that's where you were heading. Well, we do have a check. Is this the same pointer? But of course,
Is this something yeah, I mean, the general question is the way that you describe
effect handlers, I can hear. That's maybe we should take that offline, but it's a good.
Microsoft has something that does that. I think it's Versus that I may have the name wrong.
No, it's in the Coca from.
It's in Coca does this, so at least it's polymorphic regression is right. What data is this? It does that dynamically. I was going to ask the obvious question, it's me, which is I obviously think it's very important, especially when you want to start building data abstractions with normal Scandinavian. I like to do it. Why don't I just have a nesting of regions? You need to trust now. So this region is inside this one.
Yeah, so the outlives relation, that's definitely, other people are working a lot on this thing, using kind of a, and this is different in the sense that it's based on unification of regions, but the other work will use a kind of an outlives relation where you say this region is alive at least as long as the other one, and so on. And then you can use those properties to kind of alleviate away from having to unify, and you get rid of certain other problems. So there are two different ways of, I think, of looking at it. Maybe they can be combined. I don't know if that was.
Well, I think that. Well, I guess what I think is, I think there's a semantic issue of more, whether you're at some level you're dealing with flat regions or whether you're dealing with nested regions. And then I think there's an implementation issue, which again we find in standard type systems, DB type inference. And how sophisticated and how you do unification. I think it's sort of doing something simpler. And I know, you know, in the ML tradition, you guys have done a lot of fantastic work in extracting the regional information out of programs where programmers didn't do anything. And yeah, I guess the sort of other side has been a lot more explicit. We want to say, okay, this region containing these links is part of region that is containing the object that is the link, and we will rectify our messages you talked about here if you try and break that restriction. But then you know we can do what if we want to, we can do type stuff. You know, as was talked about, rather than talk about the allocation, because we know more about the structure of the regions the programmer is built.
I will leave it as a comment and not a question, but I think there's a lot of related work. I have not mentioned at all other people's work, but this is kind of the work mostly in what this is based on. In particular, the region inference algorithm by Toft and Birkedal, and also the unification and polymorphism in region inference. And then there's a lot of other slides, but I will just skip those for the sake of time. I think we took the question. If there are any questions, of course, you're welcome. I'm very interested in getting further with this stuff, but I think we have another speaker. I don't know. Yeah. Okay.
Everything requires.
Yes, so I just wanted to ask what the
mention of.
Do you have any some like remarks?
Right now.
The two remarks I have is mostly kind of relating this notion that we need kind of a small step semantics for one, and we also need the source. Because otherwise, to be able to reason about this notion
How do I?
that will require during execution, not just at the end. The original work by Costa, that was big steps.
Probably oops.
So you don't get any properties during. So this, I think, is something, and going back to also Nelson's work on biosimulation for region calculus, that is also that is a small step semantics, but it doesn't have explicit sort. That means that you will basically substitute into expressions, and it's very difficult to see whether you have sharing. Right? You need to have a notion of sharing incorporated to be able to say whether something takes up more space. So it seems that you need kind of words of both being that's well not how to do that, but this in particular the explicit sorts will take it a little bit down. You can stop
audio, right? Yeah.
And so on, and probably some perhaps previously co-induction techniques used. I think with newer techniques we might be able to. That doesn't say anything about relating to the effect handler world. Well, I read and the COCO work. I think this tradition of this thing. One thing that we should do, if one was to redesign the whole thing, I think that outlet relationship people are working on might give some additional benefits that we're not utilizing here. On the other hand, we have this work for real big systems, inference working trees for many years. That you get this substitution based approach. That gives a very fair, but with modern constraint-based systems, maybe you can get as good as that and still have the benefits. We'll have to see on that one. But this is going all the way that the compiler can bootstrap itself with these systems. That gets a lot of leeway, and it takes a lot of course, in particular the theoretical side. There's a lot of related work also outside of work.
Okay, yeah. Sorry, sorry, so please continue trying this. Yeah, thank you. Okay, so next talk is provided by the Michael. Yeah.
All right, hello. Can everybody hear me? All right, somebody make sure to give me like a 10-minute warning. I have not practiced this talk. I might go over time or under time. We'll see. But hi, I'm Mike Lawrencenius. I'm a postdoc at UC Berkeley, and I'm here to talk about finite functional programming via graded effects or co-effects. It'll turn out not to make a difference, and relevance types. So what we're going to be doing in this talk is trying to use fancy types to deconstruct logic programming into functional programming, because that's kind of a hobby of mine.
the motivation here is that I like functional programming and I like the relational model. So I like functional programming, I like higher. Is that legible to people in the back row? No.
Good.
I don't know whether there's any way to make it bigger. Well, that cuts off the top, whatever. Yeah, I like higher order abstraction from functional programming. I like his ability to do modular programming. Functional programming is great, but the relational model is also great, as I was discovered from working at a database company for 2 years. It lets me separate what I'm doing with my data from how I'm going to be representing it or how it's going to be executed. And we know a lot of good, efficient strategies for executing relational style queries efficiently. So I want data log, but with higher order abstraction and modules, and this is work in that direction.
Maybe this is a bit pedantic, but I noticed you say functional programming, but you say relational model.
Yeah.
You don't like programming. Relational programming.
I mean, I like relational programming because I like the relational model. I don't like the inability to do higher order abstraction. Yeah, and also this work came out of my time at a company called Relational AI, which was building a data log with higher order features that looked a lot like, if you squint, the language I'm about to present here, but it was all implemented as basically macros that took your higher order stuff and turned it into first order stuff that was crunched on by a data log engine. And it worked remarkably well, and I didn't understand why. Why doesn't this pile of macros come apart at the seams? This is my attempt to figure out why this thing might be reasonable to do in the language of type theory, because that's my native language. All right, here's a logic program. We're trying to model a social network. We've got a follows relation that says, you know, this user follows that user. Ada follows Bob, Ada follows Charlie, Bob follows Ada, a lot of other facts in that vein. Okay, so when are two people mutuals? Well, X is a mutual of Y when X follows Y and Y follows X. Pretty simple. What is a relation? It's a function into Booleans. It tells you whether a thing is in the set or not in the set. I know about functions and I know about Booleans and I can do those in functional programming languages, so what happens if I just do that? Follows is a function that takes a person and yields a Boolean. Follows x, y is true if x is Ada and y is Bob, or x is Ada and y is Charlie, or x is Bob and y is Ada. You just write down a bunch of ors and ands. That denotes the same set that's denoted by follows on the left. How about mutuals? I can do that too. Mutuals xy is follows xy and follows yx. So these programs should denote the same thing. They do denote the same thing, but they don't feel like the same program. And that's because I can't do the same things with them. In logic programming, or databases, or relational programming, whatever you want to call it, I can do things like enumerate all of the inputs for which a relation is true. Or for instance, I can find the mutuals of a given user. I can say, hey, who are Bob's mutuals? Functions are input-output black boxes in functional languages. I can't do this. I can pick two users and ask whether they're mutuals, and then it will do this very slow backtracking search through all of the possible matches here. Imagine there's a million things here, or a billion, right? It will give the right answer, but it will be slow, and it does not let me enumerate things. It just lets me test. For an example of where this analogy completely falls apart because of this inability to enumerate things, let's say, like, on the left, we've got a logic programming, which says, like, this director has worked with this actor if there's some film that the director directed that the actor acted in. Easy peasy. This is a relational join. Okay. In functional world, sure, I can assume I have these functions, and then I can define directed actor how exactly? Where does this film variable come from? Well, what's the semantics of the thing on the left? It's true if there exists a film such that the body is true, such that the director directed the film and the actor acted in it. So if I imagine a magical exists function that takes a function from films to Booleans and tells me whether there's any film that makes it true, then I can write this easy. All right, does there exist a film that the director directed and the actor acted in? But how do I implement exists? I need to, like, enumerate all possible inputs to it, and this is just a bad idea. Maybe there's only finitely many films, but there are a lot of them. I don't actually want to test every single film. This is not how the logic program works. It's not how a relational join works. So what I want is that this function from film to bool has to be able to tell me what are the inputs on which it is true. I want functions that aren't just input-output black boxes. I want functions that can tell me what inputs they yield true on, or what I'm going to call their support, the inputs they produce something interesting on. I'll define this precisely later. In this talk, I'm specifically going to focus, because I am data log pilled, on finitely supported functions. So how do I enumerate the results? I have a freaking table of them. I have a table of all of the input-output pairs that are interesting. Okay. Everybody good so far?
Maybe a general question. So you say you model relations as functions to booleans in the functional programming. Another option would be like more like non-deterministic functions, like using the list monad.
That's another way of saying it. It's not the way I'm doing it here. Maybe we can talk about the pros and cons at the end. I like thinking about them as just functions because it lets you be very direct about what you're saying. It looks nice. It's maybe an aesthetic opinion. But yeah, there's definitely a monad hiding here, kind of. Okay. Any other questions, especially anybody confused? If you're confused at some point, do not hesitate to jump in. I may defer other questions to the end. Okay. What do I mean when I say the support of a function? Well, we've got sets. I hope people know what sets are. If you don't want to talk about sets, you can talk about types. I don't care. A pointed set or a pointed type is a set with a default value, which I'm going to call nil. So with Booleans, by fiat, the default value is false. So then a supported function, the support of a function into a pointed type, a pointed set, is just by definition the inputs on which the output is not nil. Right? So these are the interesting outputs, right? Nil is the boring value, and everything else is interesting. And then a function is finitely supported if its support is finite. And this is how I'm going to write the type or set of finitely supported maps from a set to a pointed set. Also, this type is pointed. Its point is the function that is everywhere nil. That is the boring function. This will be useful later. Where later, I think, is the next slide. Okay, why am I bothering with pointed sets instead of just using Booleans? This was about logic programming, right? Like, all we need is Booleans for logic programming, right? Yeah, kinda, but there's several good things that come out of going beyond the Boolean black and white world. First off, it's going to let us give interesting types to or and they will be different types. Or and have different types, which I just find really cool. We'll get to it. This also allows us to curry things, right? So I can speak of a finitely supported function into the space of finitely supported functions. This is a natural way of talking about finitely supported functions of multiple arguments, and we're functional programmers. We know the value of currying. I'm mostly not going to talk about these things, but it also gives us a natural story for aggregations, which are finitely supported functions into, I don't know, like the reals or the naturals or some type that isn't Booleans. And it lets us do weighted logic programming. And there's been a bunch of interesting work here using semirings. So I like these reasons, but in this talk, we'll mostly see these reasons. So the goal here is a language that looks functional and is functional. It has procedural functions, including higher order ones, but it also has a type of finite functions, right, which are guaranteed to be finitely supported by the type system, which are going to be represented as tables, and which are going to be computed like database queries. And I'm mostly going to focus on this in this talk. I have ideas about this. Come talk to me afterwards, but the talk's mostly about one. Here are some examples of what programs in this language should look like. Right? Like I can define when two people are co-stars, and this should be, finitely supported in 2 arguments, right? When are they co-stars? If there is a film that they both starred in. I can find the number of films that an actor has starred in. This is also finitely supported, but it's into the naturals. This is an aggregation. It says, take the sum over every film when the actor has acted in it, produce 1. Otherwise, implicitly 0, because 0 is nil for natural numbers. And as a stretch goal, which I will not be able to get to into this talk because I don't know how to do it, I want recursion. I want to be able to define these relations, these finitely supported maps, recursively. So like, let's say, talk about people who are connected through the graph of co-starring in films together, which will be, just about anybody. As it turns out, all actors have, are connected to all other actors. So when are two people connected, right? When is there a path from them? If they co-starred together, or there's some intermediate actor Z, such that X co-starred with the Z, and there's a path from Z to Y. Yep. Ask that question at the end. Okay, how are we going to do this? How are we going to come up with a type system for a language like this? Our first insight is that this thing, this type of finitely supported maps, is a graded co/monad, by which I mean it's a graded monad and also a graded comonad. So what is a graded monad? And what is a graded comonad? Well, they're kind of like monads, right? A monad we might think of as like, forget about this subscript A here, right? And pretend all these isomorphisms are arrows going to the right. I have a return function that takes a P and produces a TP, right? It embeds the thing in the monad T. And then a join function, or oh, I called this return, that's wrong. Join, that takes a TTP, a computation that yields a computation and produces just a computation. Okay, a graded monad is when actually there's a subscript on it, and that subscript acts in an interesting way. There's some identity thing. When I return, I get T with the identity annotation, and when I join, I multiply the annotations together. So here, our annotations are themselves types. They're sets. The identity is going to be the unit type, and the way to combine them is going to be take the cross product. Right? And so what is going on here, in fact? Well, not only do we have arrows going this way, which is the monad direction, these things are all isomorphisms. We have arrows going in both directions, which is why it's also a comonad. So what's really going on here is like, look, if I have a pointer type P, that is isomorphic to having a finitely supported map from the unit type into P. Because like, there's only one input. What's the value of that input? That's the P we're talking about. And the other direction is just currying and uncurrying. If I have a finitely supported map represented as a curried thing, that's the same as having a finitely supported map whose arguments are pairs. But the reason this is nice is because graded monads and comonads have been extensively studied, and we have typing rules for them. And I will sort of be using those typing rules, but they will look funny. But there's another thing that we need to be a graded comonad. We need this thing to be a functor. We need it to have a map method. What is map for this type? The naive answer is, okay, give me a function from P to Q, give me a finitely supported map into P, I will apply this function to every one of its values and get a finitely supported map into Q. Except I won't, because this is not guaranteed to be finitely supported. Why not? Well, let's say the function that I'm mapping over the values just returns true all the time. True is not nil, it is an interesting value. No matter what my initial finitely supported function was, I get the function that's true everywhere. That's not finitely supported. So what I really need is that the function I'm mapping over it should preserve nil. It should do nothing to boring values. It should not touch the things that are not in the table, right? This guarantees that I only need to apply the function to things actually in the table. Everything else was mapped to nil, and it preserves nil. So let's talk about functions that preserve nil. Yes?
Just making sure I understand. So the monad is only defined over pointed sets, and map is only defined for functions that preserve nil. So what you're saying is it's a graded comonad in the category of pointed sets, not in the category of sets.
Correct.
Okay.
Yeah. So we need to talk about the category of pointed sets and point preserving maps, or nil preserving maps, which are just functions on pointed sets that preserve nil. F of nil is nil. Okay, this is not only a set, but a pointed set, which is good. Nil is, again, the function that's nil everywhere, the boring function. And now we can talk about the type of map. Map takes a nil preserving function from P to Q. It takes a finitely supported map into P, and it produces a finitely supported map into Q. And it also preserves points in all of its arguments. So just like you said, It's a functor on the category of point preserving maps. And this is useful because this is how we manipulate values that are in our finitely supported maps. Or, well, this is the one of the ways we do it.
The first thing, right, was just like nonsensical.
Yeah, that's just incorrect. That's why it has a big red X next to it. This is the type you might naively write down if you, yeah. I mean, I think I did write this down at some point, and then I was like, wait a minute. Okay, so going back over all the stuff that we've developed so far. What time is it? Okay. If A and B are going to represent sets, P and Q stand for pointed sets, we have 3 different kinds of function. We've got regular old functions, which I'm mostly not going to talk about. We've got point nil preserving functions. Both of these you should think of as being procedures, closures, normal. And then we've got finitely supported maps from a set into a pointed set. These you should think of as if they're tables. What are our typing rules for pointed sets and point preserving maps? Is lambda x.x a point preserving map? Yes. If I feed it nil, I get nil out. It preserves nil. How about lambda x.true? Anybody? I see some shaking heads. Yes, there's a big red X next to it. It does not preserve points because if I feed it nil, like false, for example, I get true, which is not nil. It doesn't preserve nil. So that's interesting. This tells us our type system is funky. Normally, you can write constant functions. How about lambda x.foo(x) and bar x, where let's assume foo and bar are point preserving, or nil preserving. Well, if I feed it nil, foo(x) will be nil because foo preserves nil, and bar x will be nil, and nil is false, and false is false, and false is nil. So yes, I get out nil. This is an interesting type system. I have to use my variables. I'm not allowed to not use them. I'm not allowed to use constant functions. But it's not linear types. I don't have to use them exactly once. I can use them multiple times. That's fine. It's not affine types. That allows you to drop things. That would allow me to write this. It's relevant types, which is not very commonly seen. This is the type system of at least once. You must use your variables at least once.
If you have a nil function, the boring function, is that also a constant function?
So that's the one kind of constant function that is okay. So I can show you the typing rule for nil. The typing rule for nil is special. Lambda x.nil does type check. Yeah. Nil basically lets you throw, you can have any number of inputs and produce nil and you're fine. Yeah.
So it seems, at least from the 3 examples, I'm convinced that relevance is like a potential over approximation for nil preservingness, but it seems like it could be a very large over approximation of nil preservingness. Like,
what kind of over approximation do you mean? Sound or unsound or sound?
It is sound, but certainly not complete.
Yeah. True fact.
How big is the gap?
Let's talk about it at the end. It's significant. I have some ideas for how to tighten it up, but I think at the end of the world, you're gonna need either a bit of theorem proving or a bit of trust me in your type system.
Can bar be a normal function here? Because
yes.
Okay. So you have combinations of that.
Yes. The typing rules for tensor are interesting, and we are going to get them, assuming we have time. But yeah, the typing rule for tensor product is funky. All right. As foreshadowed by that previous answer, there are 2 kinds of products here, as you might expect from a linear logic-like thing. There's 2 kinds of interesting products in category of pointed sets. The simpler one is with or direct product, which the values are just pairs. And the nil is just the pair of nils. Easy peasy. Or has the type bool with bool, point preserving map to bool. Because it produces nil if both of its inputs are nil. And that's kind of the idea of this kind of product. It is useful for representing functions of multiple arguments, which produce nil if all of their arguments are nil. But that's not the only interesting kind of point preserving function on multiple arguments. There's also what if I preserve nil separately in all of my arguments. If any of my arguments is nil, I produce nil. Well, that's what and is. And produces false if any of its arguments are false. And for that, it would be safe to give and this type. It would be sound. But because the typing rules for tensor product allow us to do more, we want to give it this more precise type, where tensor product is this. Tensor product is pairs quotiented by if either of the components of the pair is nil, it's nil. So nil comma y, same thing as nil. X comma nil, same thing as nil. So the only interesting values here are the pairs where both things are interesting. So we have two products and we need different typing rules for them. Yeah.
Is it and an isomorphism though?
Yes. Okay, what are the typing rules for these things? These are not the typing rules for these things because we're still missing a context, but we're going to start with just two contexts. We've got our context of sets, which we're allowed to do with whatever we like. We've got our context of pointed sets, and we must preserve point in all of these, all of the things in this context. So our typing judgment is going to look like this. Gamma delta entails T of type P, and it means we got a function from gamma into a point preserving map from delta. The rule for width is extremely straightforward. It's literally just, this is nil if both of these are nil. So we give the same point preserving context to both of them. But the rule for tensor product is more interesting. This is going to be nil if either T or U is nil. So what I can do is I can split up my context. I can add some of it to T and some of it to U. Because remember, this context is nil. When is this context nil? If any of the things in it are nil. It's implicitly a big tensor. And that means this is nil if at least one of the things in it is nil. So if I split it up, these things are both point preserving. So at least one of them will be nil. This is a tensor product, so that means this will be nil. So this allows us to split variables up, but we don't have to. This is why I've written a union here. You could totally pass the same argument to both. It's fine. That's why this is relevance typing, not linear typing. Yeah?
In the gloss there, the delta is the tensor product of everything in delta.
Yes.
Okay, cool.
Yes. That is important, and I didn't write it.
So if you have an empty delta context, there are no nils in it. There it's not.
The tensor product of nothing is Booleans. So there's two things you could substitute into that. You could give it false, in which case your result has to be nil, or you could give it true, which is the interesting case. Yeah. The identity of tensor product is Booleans, which is a bit weird. The identity of regular old product is the singleton type, which only has nil in it. I recommend not thinking too hard about the empty context if you want to get through the rest of this talk. All right. What else have we got? Okay. I've written down this typing rule. Oh God, right. Now, I wanted to write down lambdas, which stood for finitely supported maps. So I need 3 contexts. I had 3 types of functions, so I need 3 contexts. So we're complicating our typing rules again. Now, we've got 3 contexts, and this means a map out of gamma, a point preserving map out of the tensor product of the deltas, a finitely supported map out of the product of the omegas into P. Here is our typing rule for width. It is, again, very simple. Yeah?
You can take it at face value if it's helpful, but can you give any intuition of why it's this particular order of contexts when I'm elaborating into an arrow? Like, why is it that order of arrows?
Because that's the order that made my example programs work out. In fact, I think that you're going to need an arbitrary sequence of alternations between deltas and omegas, but I didn't want to make these typing rules even more complicated. Yeah. Yeah. But most programs seem to be typable with just this. So this typing rule is still like you just pass the same context to all of them. It is worth thinking about why it has support, right? What is the support of this thing, right? These things are supposed to be finitely supported. Okay, so if we have some value for gamma and some value for delta, and we know the support of T at that gamma and delta, and we know the support of U at that gamma and delta, what is the support of the pairing of T and U? It's the union. because this thing is non-nil if either of its inputs is non-nil. But the union of finite sets is finite, so we are fine. Okay, I'm going to be a lot less precise about tensor product because there are many more rules. Which of these functions ought to be well typed? Which of them actually has finite support, assuming f and g have finite support? F of x and g of y, one thing, f of x and g of x, and f of x and x is above 17. Anybody want to guess? Are there any of these that are ill-typed?
Last one.
What?
The last one.
Good guess, but no, none of these are ill-typed. They are all finitely supported. Why? What is the support of this thing? It is the cross product of the support of f with the support of g. Because, well, I mean, it's non-nil if f of x and g of y are both non-nil, and it's producing an x and a y. Support of this is the intersection of the support of f and g, right? In order for this to be non-nil, both of these have to be non-nil. The support of this is the support of f filtered by being bigger than 17. And I can take a finite set and filter it by anything I goddamn well please, it's still finite. So all of these are finitely supported. And they all need different typing rules. Okay, what's the typing rule for this thing? Or rather, they need an escalating sequence of increasingly interesting typing rules. The typing rule for this thing is sort of just, okay, I'm passing part of my context, my finitely supported context, to T and part of it to U. Why is this okay? Well, you can think of it as being because I have a finitely supported, a point preserving map of this shape, right? Or you can just think of it, I'm not going to go into that. You can just think of it as like, look, the support is the cross product, right? So plainly, I can pass part of my context over here, part of my context over there. Each of these is finitely supported. The support of this is the cross product. That's still finite. How about this one? This is justified for a slightly different semantic reason. It's justified because the support is the intersection. So, you know, I take the union. That's basically the same as for some of them I'm commaing, and for some of them it's the same thing. So the interesting addition of the previous one is that I can let the indices of my graded comonad be the same, and I still get out this thing. And then the final one says, hey, look, if my first thing finitely supports this set omega, I can actually then use those arguments however the hell I want to. This omega 1 moves, it jumps contexts from the finite support context in my first argument all the way over to the unrestricted context in my second, which allows me to apply an arbitrary function, not finitely supported, not point preserving, nothing, just any old function you want in the second argument, because you're just filtering down the support of the first argument, and that's fine. So this is a combination of filtering down and cross product, and also intersection. So this is the most general typing rule.
This is like the notion of query safety databases.
Maybe? I'm not familiar with that, despite saying database, database, database.
It's just the idea that the relational algebra in doesn't produce infinite results.
Yes. Yeah, exactly. That's what I'm trying to ensure.
So it's not commutative?
What?
So it's not commutative?
Haha. I have chosen not to make it commutative. In principle, it should be commutative, but I didn't want to make the typing rules even more complicated. Yeah, so you have to think about the order you put things in to make sure things ground from left to right.
So isn't first rule and the second rule the same?
No. Because in this rule, the variables have to be distinct that I've passed between them.
Yeah.
Right? Whereas in here, I can have the same variable appear in T and in U.
Sure. Let me rephrase it. Isn't the first rule a sub-rule of the second rule?
Yes. Yes, this is more general.
Okay, yeah. But the third rule is not more general.
I think it is, actually. Find me a counterexample.
Like, what is the third rule need to be a union?
I don't think you need it to be a union, because I think you can always just pick all of the variables that occur in U that occur in P, and put them in omega 1, and they go here. Yeah.
Yeah, okay.
Yeah. All right, so what the hell is the typing system we've come up with here? Yes?
Still the terms to witness
I conjecture that you can always find an order to put them in by using let expressions so that it grounds properly, but I don't have a proof.
So, I mean, that often happens. You can still like laboriously sort of rewire things.
Yeah.
Particularly like session typing systems where we have hats are interpreted in a strange way.
Interesting.
Send an A and then behave like B. It looks like it's not used to the thing.
Yeah.
But it still derive the
Yes. Yeah, although here it's non-commutativity on the level of sort of the terms, right? Like the order in which I put my term in might make a type check or not, but you can always, I think, find a program that makes a type check that has the same semantics. Fingers crossed. Okay, what is the type system we just come up with? So far, it looks kind of like it's just relevance typing again, but with that weird funky last rule. But it's not. Let's look at our examples to figure out why. Here are our 3 example functions. Here's whether they preserve nil or not, assuming foo and bar do. Now, if we assume foo and bar are finitely supported, which of these are well typed? There's exactly one that's different. There's exactly one that is different in this column versus this column. Anybody want to guess? Yeah?
Identity?
Correct. The identity function is not finitely supported, right? Take like the function lambda x.x from the naturals to the naturals, where 0 on the naturals is I don't care, like 0, nil on the naturals is 0. That has infinite support. All of the naturals other than 0 are in my support. It's not finitely supported. It's also not even well-kinded. Finitely supported maps are supposed to be from a set to a pointed set, but like this is from a type to the same type. They can't. So I can't even express that. But even if I could, it would be wrong. But this is well typed. So what's going on here again is I've made this context, but it doesn't correspond to a category. There is no identity map. It corresponds to a graded comonad. So what do my typing rules look like? What are my introduction and elimination rules for finitely supported maps? The intro rule is very boring. To make a lambda x.t, I put x into my finitely supported context. That is what it is there for. It's the elim rule that's funny. The elim rule says, if I have a finitely supported map, I can apply it to a variable, and then I can throw that variable away and check that this is finitely supported. So the way you eliminate finitely supported variables is you apply a finitely supported function to them. You ground them. You make sure that there's only finitely many values they can take on such that my expression is not nil. So the way you get finitely supported maps is from other finitely supported maps. Which means you need some primitives that generate finitely supported maps, or else the type is empty. But this is still not quite right, because I put a comma there. What if I want to take some function and apply it to the same argument twice? This is actually perfectly fine, right, in terms of support. So I need to make that thing a union. And now I can take a finitely supported map of 2 arguments and apply it to the same variable twice to diagonalize it. So, okay. So how do I actually make finitely supported maps if the type system doesn't, let me write down, doesn't have a variable rule? Well, here's one way. Equality. Give me a value. There is a finitely supported map out of that type into Booleans that is true exactly for that particular value. More generally, if you give me a value, a key, and a value, then there's a finitely supported map that is nil everywhere except at that key for which it produces that value. It might be nil there too if you happen to give it nil, which is why this is a point preserving map. Then there are a bunch of functions for combining things. We already saw or and. And so, you can use those to combine maps that you already have, right? That's what foo(x) and bar(x) is. It's an intersection of sets. You also have a function like when, which says, look, if I've got a Boolean and a value, well, I'll give you nil if the Boolean is false, and I'll give you the value if it's true. So this we saw way back in some of the example program I wrote about summing up all of the films, right? Finding how many films an actor has appeared in, right? We also have a whole family of aggregations, right? So we saw exists. If I have a finitely supported map from some type into Booleans, I can tell you whether the support is not empty, right? Like, look at the table. Is the table empty? Then false. If the table has a thing in it, then true. But also, since the table is finite, I can sum up all the entries in a table whose values are natural numbers. Or I can take the minimum of a table whose entries are natural numbers or infinity, and infinity is the default value, because infinity is the identity of minimum. Yep.
Can exists work with a different pointed set other than bool?
That's what these are.
Oh, yeah, okay.
Yeah, that's the idea, right? Things that have a type of this shape, right? A finite support into P, point preserving map into P, are aggregations. This is the story for aggregations. And in fact, one can conceive of a type class, right, which is things which are additive in this way. I need a function add that takes P with P to P, which has the property that adding nil does nothing, and it's commutative and it's associative. And then I can lift that to a summation function that sums up all the entries in some finitely supported map. Yeah.
I'm able to do some other kind of product. Does that fit into this pattern somehow?
Product is point preserving with identity 1. So it would fit into this if you had the naturals where the point is 1.
Yeah, as you said, it's the type actually point.
Yes, the type contains the point, which is awkward because there's a lot of possible points in the naturals. Right? How do I define types? I don't have, I don't have a great story for doing that. So this is the bit where there's a gap between like soundness and completeness. It's like, how do you get all this information into the type system? So at some point, some sort of trust me feature where I just define some trusted primitives and everything else works out compositionally. And like, there's even an example here. I say, if I have an add satisfying these laws, then I can get a summation function, but I can't define that inside this language. It needs to be a language primitive to lift an add, which is associative, commutative, and preserves nil into a summation function. 10 minutes, cool. We're nearly done. So what this talk should have been called was Lambda, the ultimate relation, but I didn't think of that. The one thing you take away, if you take away nothing else, is relations are functions plus support. Relational programming is functional programming where we care about the support of functions, where they're not input-output black boxes. They can tell me the inputs for which they have an interesting output. I've talked about finite support because I am a data log head. I suspect that the same story would work if you cared about innumerable support, and then you'd have something that's kind of like Prolog. I think this approach is nice because it naturally handles weighted logic programming, which I think is cool, and aggregations, which I think are very practically important, although only some aggregations. Aggregation is hard. The type system is ugly as hell, but I love it. It is the funkiest type system I've ever thought of, and there's no dependency in it. Don't have to have dependent types to have an interesting type system. It's got graded comonads, it's got an adjunction. There's an adjunction between set and pointed set that I didn't talk about. It's got relevant types, and it's got a lot of fiddly little details. And there is more that I did not talk about. And with that, I'm going to open up the floor to questions.
Would you mean by enumerable? Aren't all finite sets enumerable?
Oh, I mean, if you wanted to loosen it from being finite to being enumerable.
Oh, I see.
Yeah, yeah, because in Prolog, your relations aren't always finitely supported. Yeah, although I'm not sure even enumerable is correct for Prolog because it can represent like, you can just define a predicate that's true everywhere in Prolog, which is not necessarily enumerable. I mean, like it is if your type itself is enumerable, but like it's some sort of more symbolic representation of the support.
I think Prolog was a very nice sentence.
I don't want to answer that question.
I asked about recursion.
Oh God, yes. Why is recursion hard? So, okay, no, I'm not going to go all the way back to where I mentioned it because. Well, I think recursion is hard because it means various different things. And so depending on what you want, you need to figure out how all those things interact. So in data log, when we define relations recursively, what that means is sort of you have a rule for defining the relation based on itself. You start out by feeding it the empty relation, and then you get a slightly larger relation. You feed that in, you get a slightly larger relation. You do that until you get a fixed point. So it's sort of bottom-up fixed points by iteration. I know how to do that. In functional programming, what fixed points mean is basically laziness. I define a function with respect to itself, and that works out because it can't call itself until you call it. And then you add non-termination in order to make it all work. That's no problem. But how do I combine those? I don't really know. Because now I've got non-termination mixed up in my fixed point loop.
Function 25, you have to.
I think so. The problem would be ensuring termination of your fixed points, your bottom-up fixed points, your recursively defined relations. Because as soon as you have the ability to add 1 to a number, you can define an infinite relation, right? I can define like foo holds of 0, and if foo holds of x, then it holds of x plus 1. That's infinite, and therefore kind of non-terminating. And so how do you forbid that? So ensuring totality and having recursion is hard. And for the functional programming side, we know how to do like inductive things, and we can ensure termination there. I don't know what a nice equivalent story. I have some ideas about that. But I don't have a nice equivalent story for relational recursion. And I kind of don't want to. I'd rather have general recursion. I want a story that works for general recursion.
Isn't it a lot easier, maybe it's not, theoretically, if we think about enumerable things rather than finite things, because then you don't have the +1 forbidding problem?
It makes some things easier, but it makes some things harder. Like if the support is enumerable, and then I take the sum, that could be infinite.
Yeah.
So you could just say, well, if it's infinite, you're hosed. And that would be one approach.
Why not have yet another sort and effect system? We need an effect system. That's just fun.
You could try that. You could try to know whether your things are going to be enumerably supported or finitely supported and put that into the type system somehow.
Yes.
Ugh. Yeah.
So on the slide where you had like the 3 different typing rules for tensor increasing generality, I noticed that like on the first 2 you had like, oh, here's some nice category theory words that are explaining what's happening. For the last one, there was no. So I'm curious if there's like a principled way that you like arrived at this rule. I think there is some like more interesting like math going to like justify why this like works.
Very roughly, I don't know. I arrived at it by looking at this function and saying, yeah, that ought to be grounded. That ought to be finitely supported. Like this is a totally standard thing to do, filter down a set. And I was like, okay, this seems like the typing rule I need. Can I give it a support? Can I figure out what its support is? And is it going to be finite? Yes, I can. I did not have enough space on the slide to fit in the showing that its support is finite, but it's not too hard. Is there some categorical account of this? I would love to hear of it if there is one.
So you introduced the graded monad/comonad. One important thing is what are the assumptions you place on the algebraic structure that forms the grades? So that question, does it relate to the settings that you mentioned in one of the possible applications?
No, I don't think so. In this case, the grades are types, or in practice, they're going to be contexts because that's how I'm using them in my typing system. And so I am being a little fast and loose here because like normally in a graded comonad, you need the grades to form a monoid, but A cross B cross C is not the same type as A cross B cross C parenthesized the other way, but they're isomorphic, and these are all isomorphisms, so it should work out, I hope. Wave hands here. But I don't think it's connected to semirings. Semirings actually go here. They're the pointed types, right? A semiring is a pointed type with an additive structure and a multiplicative structure on it that both work out together. Yeah, is that clear enough? Okay.
Just making the point that context form a monoid. So I think you're fine. You just, tensor out in the last stage.
Yeah.
Yeah,
I guess.
Yeah.
Okay.
Have you considered like allowing more interesting interleavings of, sorry, I know you considered this because you mentioned it, but are you working towards allowing more interesting interleavings of the 3 different types of arrows that you have?
I have,
the 3 zoned context?
yeah, I have like thought about it. But I haven't really worked on it because again, these typing rules are already at the limit of my ability to think pretty much. I'm trying to find the slide. Whatever, this slide has this on it, which is good enough. The thing that I think you need is, yeah, so gamma is always at the outermost, I think. I'm not even entirely sure about that. But you can definitely have like delta, omega, and then another delta, right? Because you can have a finitely sorted map from this into like a point preserving map over here, right? And those do not commute, right? A point preserving map into a finitely sorted map is not the same as a finitely sorted map into a point preserving map. You can't move the arguments around. So you need your context to reflect that. And that's basically as far as I've got in thinking about it.
So I agree that like semantically gamma does have to be all the way at the left because like things in gamma don't necessarily have a nil. It doesn't make sense to put them anywhere else. But I think syntactically it's going to be a little bit annoying. So I think your type system is a really nice typing for greater than on nats because it's the greater than function on natural numbers.
Mm-hmm.
So it goes like nat, normal arrow, nat, finitely supported arrow, O.
Correct.
So that means I think you could do with your fun typing for and, you can do great things like 5 greater than x and x and x greater than 3 is completely finitely supported and so on.
Yeah.
But I don't think you can write that for less than, which is a bit unsatisfying.
Yeah. True fact. I don't know how to solve that either.
Like, have you considered like just solving that with, I don't know, like syntax hacks where all of the gamma-like things are semantically pulled to the left, even though you could just write them wherever you want?
Yeah. I have not considered doing that because I would need a system that actually like runs examples to care about figuring out how to do syntax sugar. And this is all pretty much theory at this point.
Okay, the last question.
Yes. Have you considered an effect system in an SMT solver?
No. What would the SMT solver be for?
Well, because presumably once you have your effect system, you can then tag your functions with predicates like preserves nil or finite sorted or so on and so forth, and then just put in all the facts you're allowed to use and see if it's set.
Right.
Implement type system. My favorite categorical.
I kind of like having a type system rather than throwing an SMT solver if I can get away with it because it's much more predictable what things are going to type check. The place where I would consider throwing an SMT solver at it is for like, sometimes there's point preserving functions that I don't know how to get the type system to know are point preserving. So I'd sort of like to implement those as like little primitives, right? Like here's my custom user-defined type, here's my custom user-defined functions on it. And then instead of just telling a type system to trust me, throw an SMT solver at that little chunk of my program, and then do the rest of the program compositionally. So if I were going to use an SMT solver, that's how I do it.
But yeah, you can have your type checker just have nice SMT instances. It's like a fast cat.
Let's talk about this offline.
Okay, so let's speak again.
I don't know. Start having this multiple contexts. Figure out which ones to do. Or are they more?
Yeah.
Terrible if you kind of say, I want to come this.
I mean, it's very.
Which one you will?
I think so. If I were going to implement this, I would definitely implement it using a bidirectional system rather than trying to do Henley-Milner style magnification. Because that would mean that every time I see a lambda, I know which kind of function, and therefore I know which context to put the thing into. Without that, Yeah, I think it would be hard. Yeah. Oh no, I definitely like if you EX it wants to say that unless you've introduced the lambda finder underneath. And you know, you definitely if you the way you'd actually implement it is you'd mark it inaccessible, and then if you see it, you'd be like, no. You definitely don't want it exposing an earlier variable with the same name.
Yeah, I think at some point people panicking because we allocated so much memory. So this like conservative.
Abstractions.
A and B people are
A and B people, they can't do like.
So
Yeah,
like
okay, okay.
people for semantics.
Okay. They can.
Conventions only give us maps to Boolean.
Sorry?
And it maps into other things.
I mean.
Already so. The future. That's so things that everyone else.
Yeah.
But I was confused. Because
comprehensions.
one of the
In the same way, there is a way to do it. I'm also just interested in this because I think it's nice. I think it's nice to define these things as functions.
Yeah. So. Okay, so
but on the
are
right,
you using this in the context of aggregations? You want aggregations? So there's this thing called monoid comprehension.
Yeah, okay,
where
but
just comprehend monoids and
Yeah. On the pool, let's say,
the parameter,
generalize the pool.
So when you write T index,
yeah,
that must be
the
summary.
like
we must.
What
The other thing that I've been
Yeah.
how to implement this, I don't want to implement it in.
I don't know, like
That's how I did it.
at the beginning I had this intuition like, okay, he's talking about like I don't know, like modules, right? So you have like these two tensor product. I mean the product, the tensor product modules, and then you
modules in which sense?
In the sense of rings, let's say, but
modules of
throw away the semi-ring structure. Just keep the nil and
yeah, that's
is a story for how to do intersections actually.
Blend of mathematical.
I just everything
like some kind of
on the argument of the
because I kind of can imagine how I would include Haskell, but then I would just really forget about final presentation because I mean, like we do Haskell, we just over approximate instead of power set, we just have lists. They are sort of enumerable, cannot track finds anyway. So but then I wonder if you want to range over this one.
I do not know whether that story would work.
So then you
particular, I think you
just know that there was a lot of work on optimizing
need to
queries and
the simmering
things you can
there
are actually object-oriented databases, but
so because in Haskell I cannot
a lot of things
after permutation.
All of what you're looking for. So you're more interested in type aspects.
I mean, it's supported. Support.
So you can look at the work of
Booleans. Instead, I would replace them by lists, which would be just like sets, but permutation idempotence. So, but then if I want to replace something else, which would be like undoing bullshitting by mutativity.
Yeah, exactly.
Is there such thing?
Yeah, I think so.
I think it's Leonidas, but just L dot.
Yeah, I think.
Not sure about that.
You can. I mean, theoretically, you can.
I was gonna say, also the story they
like it would like a list of pairs where pairs
semi-rings and semi-ring dictionaries, and I think that's very relevant. It would be really cool. What I was very briefly thinking about is what would be really cool to have like a functional logic language, except that's actually an array language as well at the same time. Interesting. Just have everything language similar, especially with that connection. So have you thought about, so you thought about semi-ring dictionaries, but have you thought about, is this what you're saying before a while, I got distracted, or
So the difference there is,
Yes.
they focus on semi-rings, I focus on pointed types. I think pointed types are in general,
You said about weighted logic programming, I thought that's where the connection lies.
yeah, absolutely, right? A lot of people thought about weighted logic programming in semi-rings, but most of the work just says, okay, pick your semi-ring. Now interpret all of your programs with respect to that one semi-ring.
Yeah.
But in practice, you want multiple semi-rings and you want to switch between them.
You thought of a type system that proves that something is a semi-ring?
Yeah. Oh, God. Well, semi-rings, I think, form a symmetric monodal category, so I think you should be able to throw linear logic at it.
Yeah, that's an interesting, because I was thinking about, can I have a type system that will prove to me that something is associative or is commutative? I don't know.
That bit's harder.
Yeah. But that's what I mean by proving that something is a semi-ring. I don't know what.
Yeah.
Do you mean distributivity or?
No, I mean more. So again, in many of these things, there's a distinction between like proving that your primitive things have the properties you want, and then compositional composing things that have the properties you want into bigger things. And if I know that, say, semi-rings and semi-ring homomorphisms are probably like semi-ring modules and module maps, I don't know. If I know that those form a symmetric monodal category, that gives me the compositional side of the story, how I can compose together maps that I proved have the properties that I want. But it usually doesn't give me a nice way to build up my primitive functions that have this property in the first place. That's harder. That's where, throw an SMT solver at it would be one approach.
Datalog has accents. I thought it was amusing. They said, "Oh, there's no way to construct at this point. There's no way to construct a finally map." Like, well, yeah, in Datalog you have a statement that has no assumptions, and you create that's the point at which I say, "Oh, this is just Datalog." But I guess there has to be some sort of primitive. Like, you have to. Not everything is propositional in that sense.
Yeah,
it just comes out of nowhere.
Yeah, I do vaguely have a story about how I can define things and show that they are point preserving. Which is if you have a type where I can decide whether something is the point or not. So equality with the point is decidable. So first order types, right? Like I can do this for Booleans, naturals, whatever. I can't do it for maps from the naturals to the naturals because the point there is the constant nil function and I can't tell whether a function is nil everywhere, right? But if I can decide whether it's nil or not, there's an isomorphism between P, the type that has decidable nil equality, and maybe non-nil P, where non-nil P is P without the nil. And you can use this to define functions. It's very easy to define functions on maybe non-nil P, and then like inject them back into, turn them back into functions on P.
So it was sort of like predicated types instead of predicated types?
No, this is just like a trick to be able to define a function and then guarantee that it's point preserving by forcing it to be point preserving.
You do the case on the outside first.
Right, yeah, I test whether the input is nil. And if it is, I produce nil. Otherwise, I run this arbitrary function that doesn't need to preserve points.
So it's just the way you make a semi-ring and monolith, right? You put an option of maybe around it.
Yeah, yeah. But there is a maybe comonad in this type system. I didn't talk about it, but maybe is in the type system, and it's a comonad on pointed sets instead of a monad.
Like maybe is why, like for context, maybe unit.
Yeah, right. And one is also maybe zero.
Right, exactly.
Spence, have you thought about how to implement the type system? So at first glance, it seemed very hard because it's a bunch of units where there's like choices you have to make about where things go.
Yeah.
Then it seemed easier because maybe there's a canonical, like it's always a good idea to go one direction, but I
don't think it should be too hard. I think, like you said, for tensor product, there is always one direction that you want to go. You want to do everything, but like I think the way you want to do it is you don't want to actually split up the context and pass it to both things. You want to collect information on how each thing uses its variables. So you want to do it more like the graded type systems that I've seen, where it spits out, yeah, I used this variable once. I didn't use this variable, and then you combine that information and you see whether there's a way to make it work out. And I think if you do that bidirectionally, it should not be too hard, but I haven't actually done it.
Great. Oh, also tiny presentational thing. Unless this is the effect you're going for, the type of and looked like crazily weird. Like the typing rules for like full tensor product. But then like 3 slides later you introduced when, and suddenly it all made sense. There's no reason why I would believe when should be commutative because it's got like a bool on one side and a p on the other one.
That's true.
But if I'd known about that one like 3 slides earlier, the rule would have been easier to. I wouldn't have had such a visceral reaction to non-commutative.
Yeah, that's true. When is more general than and it's clearly non-communal. Yeah. Yeah.
Right.
Get food?
What happened to your beer?
When I saw you look on it, it's very different. Hey there.
Finally.
So where, I should get my. Long time no see. Oh, are you in the lab?
But you know, at the same time.
See you. Yeah.
Make sure that your opinions have the same pace.
No.
Yeah. Actually.
I know, just in. It's just. Research for you guys. I think. You know, including marketing and everything like this. There are. Program. Working on. Being very. Not really personal conversation, but because it's a lot of.
So for example, step start military
Which say the single sequence is just not.
Next one in programming. You know the backstory stuff. Yes. Work hard. But what is the look of that here? Simple. Edge distances and then you project range slope. No, those and so position or areas that I see students. What that's currently probably this where and then to visualize it and additionally, students are and then for she's just there's feel out bigger options that I think sort of doing a process I've been trying to figure out
Look at this, and then say start. Yeah, we thought this. I mean, we have patient emotions, most clients. It's, I thought, yeah, it was really fun. On days, I remember sometimes. The better the others, if I have to work, but I have a full-time job, as well. Yeah, it is, we don't do so I have a multi-hour commute to get on the trains to whenever I have it, even when we completely finding. Either I see any the in and out of research meetings, TA since until 5, and then we have 2. And then approval.
What's the I mean, if you kind of have stability in either programming until stop programming right now, say we're focusing more on right on the part to get it and go back to what then the plan is. So if you like most of the time somewhere mostly go in, get in and slow down the fall. Kind of good if papers ready for like conferences and like for the next year. And then I think we start working with that. Which is it's very which they can always want to be a few. So yes. Anybody perceive possibilities? Yeah. I think that's it. You really don't see. I think it's you should be out there. You said you're home. Over. Every year.
Actually follows something
Let's say, yeah.
So first, I think all there is infinite traces. The evolution is infinite, but infinite evolution there gives the infinite trace. These two examples are different because simply detect we can then detect this. So how can distinguish these two? This is yeah. Yeah. And this is also so this would set in different events. There's the spectrum of these arguments to avoid this is yes. So here we have Because we are still saying that all those things
And the message.
I just need to.
Already sent a message. Well, 20 minutes.
Characterized. Always have a bad this. It doesn't have any
Yeah. I get information, I think it's thoughts, this one that.
Yeah.
Really. Improve it. Real things makes sense. Be a bunch of students and basically resume. But you have to go reset.
Thank you.
Yeah, I kind of. And then later, you basically have been here. So I basically try to yes, but you make these. Yeah.
Yeah.
Then we look at.
It's like the live stream.
Either that's a good idea. Then let's see that. You solve the landscape.
Was it on here?
I think we started.
Okay, but let's.
Oh, they just restarted and it's not working. Okay.
In our. Some slides. No.
The slides must be trusted.
Relation to.
Yeah.
Big point. What do you not like about that?
Just a second.
I guess the Zoom system is not really. Why maybe first trade function. What's happening? We don't see why.
Yeah, right, and also in the end, so it's really that's.
I think that you should actually.
What does make paragraph work? So I can just we connect to the same website and so.
But why do you? So that we, my understanding.
I think it's paragraph down there.
It's some of the same.
Yeah, and distribution. One of the things that give me like a. So.
Yeah, I guess.
Enter the code.
Technique we're actually doing. I'm trying to make and that's also the chat is here come from them. Ideas. And you then.
I can find a USB.
Right. Then it's connected point that for effect we legally have to install we need to mark basically
points. So what you which done one word. That is not accessible by effective or by the. Let's say. Particular to how do we what mark was right?
Yeah, it's need to set.
That basically yes, you turn off no time. It's like okay, it's like that. Well, later uploads first. Everything up until that point. We need to but doesn't it mean that they basically limit the point to which the configuration is access to? Actually, you must kind of the start point to which with effect in this kind of basis. Not sure that's like a training that actually makes sense. Also, I mean, if you want to get Jonathan think about how to phrase this.
Yeah. I mean, for example, for
too technical at this point. Because but I'm asking not how, right? But why? What? That's not low yet. Let's try to get that. I've already checking because extended just remark, but I'm not sure what again, like why do I set this? Maybe context. Yeah. Yeah. And context. Okay. Okay, like set a marker starts with it's a marker in memory. The point is like not to set a marker against but to set the marker to the start. It's kind of lower. Yeah, yeah. Next, yeah, no. I guess I'm saying 20%. It's a new context. It's a the impact. So
Let's see from we have by four. We need to go first if we make a snapshot of that. It's very fantastic. So we store a good snapshot. And resume file. Yeah, this is not so for not my right here. Okay, this is kind of take a step from there, right? Yeah, that's here we then you say like this is the reference to the slide. But in particular, I would suggest remove, introduce a slide that's the one. I could tell you the exact number. You know, just to reply there. Yeah. Take a snapshot for that. And then this is basically in air. I would actually so the other side, or if that's three. If you believe it makes sense to show resume every template. Let's see in a second. So we can go just for the resume of this. That you say like okay, all yes, and to basically sort of create those. Not for the second one. Software is not that so good. What is not there is. I put some integrate the site in the without naming. So do you think that you want to basically show here? You want to basically write which I think would be set a marker where we should whatever. I think it. Yeah, but keep it. Okay, I would do it here, but yeah. So that people actually see what. And that slide you should be this. And that's fine. Yeah, I mean, there's all these restored patients that would make this like it's very one example. Yes. Just one explain. So sorry. I understand that you basically say that for me it was just kind of subtle. So for same kind of basically what the big deal was that would be so we could not refer to yes. And basically I mean maybe but super interesting, but I don't understand. I get that, but I don't understand why you explain it as part of it. Yeah. Just together. You always we will say something about return. Like that's kind of something even then later, right this stage, I'm not sure yet. Right, because it will change. But yeah, maybe you can about it. It's like what we actually doing, we want to resume the conversation. Resume. And resume is still. Right, now what we do is we still continue, but also like we don't really restore. So that we can continue. But yeah, I think this
So, are there presenter for second and third talk for the next session? No presenter here? Okay. Okay, so yeah, come here. So all right, so is there a presenter for second and third talks of the next session? Not yet here? So yeah.
The work like this?
Yeah.
I can maybe just put it here. Okay. 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 Like, I mean, is the mic working properly? Is it working properly, the mic?
Yeah.
Okay.
All right, so welcome back. The first talk of the presentation is about effect currency. So maybe we will also present it in ICFP.
Yeah.
Okay, so please.
Okay, so hello everyone. I'm going to present our ongoing work, compositions for free, reasoning about effectful lenses. So to begin with, let's consider a very familiar problem. If we have a pair of two functions converting back and forth between two different data types, A and B, when are these two functions consistent with each other in terms of synchronization between the two data types? The answer is obvious when they form isomorphisms, right? So specifically when they are inverse to each other. So the problem is, what if we introduce effects into the pictures? We introduce effects into the two conversion functions. So now our question becomes, can we still use some form of inversion to characterize the consistency between two effectful conversion functions? So we have a pair of Kleistli arrows here. The answer is yes, of course. So we can just move from the category of pure functions to the category of Kleistli arrows, right? So we replace the function composition with Kleistli composition and replace the identity function with the pure arrow. And sometimes we see that specifying that f followed by g is equal to pure is not enough. It's too restrictive because it requires g to cancel all the effects of f. So we can further generalize this by specifying a predicate p over the composition of f followed by g. So it seems everything is done. But we also need some structures over effectful bidirectional programs. So for example, with the formalization here, we can see that it forms a category, right? We have an identity arrow and we have a composition for these isomorphisms with effects. And beyond that, we also have further structures like the product and sum. So we also. Yeah, sure. Ah, right, okay. I think entire screen works. Okay. So where were we? Yeah, right. So we also need combinators for supporting sum structures. Right. Okay, yeah, okay. Okay. Right. So we also need some combinators to support compositional programming for these effectful isomorphisms. Like if we have a pair of functions converting between x and y, we can use the first combinator to make another synchronization between pairs so that the functions are used to transform the first component of the pair. And similarly, we can also have combinators for sums. So the two pairs of transformations are used respectively to transform the left and right branch of a sum. So the problem is to characterize the interaction between two effectful computations, and to establish some nice structure about this interaction. And it should also support combinators such as product and sum, as we have just shown. So if we just use the classically composition, we can start reasoning with monad laws, right? So for example, for the first combinator, we consider first F followed by first G. Then we can first expand the definition of first F and use monad laws, specifically here associativity, to rearrange things. And then we eliminate the pure by using identity, and then expand again, and then rearrange. So we see that first F followed by first G is inverse to each other if and only if F followed by G is inverse to each other. But the problem here is that when we use different monads in the two directions, now all of a sudden we cannot compose F and G together because we no longer have the classic composition. They are different monads. And it is well known that composition of two different monads may not still be a monad. So in our ICFP paper, we used an approach by working without the composition. We used a relation called the round-trip relations. So this relation is a generalization over pure function inversion. So for pure functions, we say that G after F is ID, is saying that G and F are inverse to each other. Then for effectful computations, we say RFG is the relation for first run F and then run G, and we must get back the original input. So it's a direct generalization of the inversion relation. And for this relation to make, for it to actually describe something that's meaningful, we need a set of laws or axioms for this relation. So we had identity, composition, and these two for the category structure. And we also have product and sum to support the product and sum combinators. And finally, we have this very exotic looking, but still necessary axiom, which specifies a very specific situation. So if we look into this axiom, we see that two pure computations, F and G, are happening in between the composition, right? So we have lift F and lift G happening in the middle of the composition. So really, if we can compose the two classical arrows together, so if they are using the same monad, then sure, these two are equivalent, right? Because they compose to the same thing. But because we don't have the composition structure, we have to use an axiom to specify that this is true. So by checking all the axioms, we see they're really calling for a real composition structure between the two classical arrows using the two different monads. So let us be clear that these axioms actually serve their purposes well. So they really support a rich combinatorial language, and they are shown to be satisfied by all the common effect combinations. But there's one problem, is that we are really doing the composition. We're composing two arrows without saying that it is a composition. So what we want is a real composition structure, which will make most of these axioms redundant, okay? So let's introduce the free composition. So while working towards a composition structure, we consider this bind operator, which is missing because M and N are different monads. So we don't have appropriate monadic bind operator for this, but we can try to do as much as possible to combine the two. So recall that for a monad, a bind is just a functor mapping followed by a join, right? So the join is the monadal structure in the endofunctor category. So for this specific setup with M and N to different monads, there's no join, but we can still map. So we have this bind operator decorated with daggers, for lack of a better notation. We cannot join, but we can still map. So we just use fmap to combine the two things. And if you are familiar with the Yoneda lemma, you can see that this is an instance of the co-Yoneda lemma, right? And here we introduce this new symbol O times, which is exactly the same as the regular functor composition. So F O times G is just F composed with G, but we use this symbol to highlight the boundary between the two functors. So on the left-hand side of this operator, it's the effect for the forward direction. And on the right-hand side of this operator, it's the effect for the backward direction. So we make this clear by using a different symbol. And if we consider a chain of effectful computations, we see that we can combine M and N into the composition M composed with N. And we can also extend this composition on the left with M and on the right with N with these trivial definitions. So it might be even more intuitive if we consider the composition in terms of join instead of bind. So if we think of all these compositions in terms of join, we see that the first composition is just an identity. It's lifting from M composed with N to M composed with N. So it's an identity. And for the other two, it's really just absorbing the extra M or N into the composition structure by using the respective join for the respective monad. But the problem here is that it's not really a monad. It only allows certain compositions. So for example, we cannot extend on the left with an N or extend on the right with an M. So it's not strictly a monad, but still it's some structure. And as it turns out, it's actually a polymonad. So for most of you, I guess you won't be very familiar with polymonads, so I'll give you a quick definition. A polymonad is just a generalization of monads. So first we have a collection of functors. One of them should be the identity functor. And we also have a collection of bind operators. It is, or equivalently, the join operators. It combines M with N and it gives rise to a P. And it only works for certain triples of M and P. And by using this bind, we can derive the F map operators and the monad morphisms, those lifts. And polymonads also have laws, which are generalization of monad laws. And among them, there's the associativity law. So it turns out that the composition we just defined actually forms a free polymonad. The monad has this collection of functors, the identity, the two monads M and N, and the composition M composed with N. So by being free, it means for every polymonad with the composition which can compose M and N into a P, we have a unique lifting from our composition to their composition P. And this lifting is just by binding with ID. Just like for usual monads, you can define join in terms of bind with ID. And the property for this lifting is that it preserves the polymonad compositions. So it preserves all the composition structures. And this result follows from the associativity law for polymonads. So what's the significance of this structure being free? It means we have maximum generality. So as long as there's a property can be formalized on some notion of composition, as long as can be formalized using a polymonad, it can also be formalized based on this free composition. So it means we have full generality. So let's see how we can reason about these effectful computations using this free composition. First, we had the identity and composition laws for the round-trip relations. Now we can also have the identity and sandwich law for this free composition. So this P predicate accepts two things, a value X and a monadic action M, or actually it's not a monad. It combines the two monads M and N. And it basically says this action M behaves like X. So it returns X and it does some effects, but it doesn't disturb all the other effects. So it behaves like pure. And the identity just says that pure if the two directions are both pure, then sure, it satisfies P. And sandwich law says that we can extend an arrow F on the left and on the right with two other computations with the respective types. So that's all very natural. And what's good about this new formalization is that all the other axioms become theorems, so we can actually prove them. For the product, as we just saw, using the first combinator, we can start with this composition and do basically the same as in the monadic situation. We just expand the definition and use the associativity law and identity law, and then expand again, and then use associativity with identity to have this sandwich structure, which fits directly into the previous sandwich axiom, where we can apply that axiom and simplify everything so that the composition of first F and first G follows from the composition of F with G. And we have a very similar situation for sums. So we can still start with its composition and expand by definition, reassociate, eliminate identity, and expand again, and form this sandwich structure where we can apply the other axioms and get the theorem we want. So these are how we can reason about the composition of two effectful computations using this new free composition we just defined. And now we can see some examples for how we can specify useful properties over the composition between different effects. So we start with something simple. We consider the error effect. So from this definition, we can see that the forward direction uses the effect error E, and the backward direction uses error E prime. So they are different effects. And so the forward direction can report the error E, and the backward direction can report the error E prime. We can have a strong specification over the interaction between the two directions by saying that if the forward direction fails, then everything is fine. Or if the forward direction succeeds, then the backward direction must also succeed, right? So that's an interaction between two formal computations. And we can also weaken the conditions by saying that even if the forward direction succeeds, we can still have the backward direction fail. So this relation then says that only if the two directions both succeed, then we have the original input value recovered. Then after that, we can also consider some other common effects like the reader for a shared context, right? So usually we can consider this reader in terms of the reader monad transformer, this reader T. And here we can define the predicate by lifting the base property P0 to the property P on the reader effect. So suppose we have some specification over the interaction between the monads M and N, then we can lift this specification to the interactions between reader T as M and reader T as N. So this lifting can be just directly defined by interpreting the two reader T effects and supplying them with the same context S. So this lifting really says that the two directions share the same context S. And all the other things are delegated to the base property P0. And similar to reader T, we can also define something for the state T transformer. We still lift some base property P0 to P. And the interpretation just says that if we thread the same state through the two directions, the state must also be recovered. So we are treating the state as part of the input and the output in the base property P0. Right, okay. So that's all the examples I have for today. And we can conclude by saying that different monads can still be composed for free, but we do not get another monad from the composition. instead, the composition forms a free polymonad structure. And the composition is performed in sequence. So it means first we perform the effects from the first monad M, and then we perform the effects from the second monad N. And we can reason about this composition just like normal monads, using all the familiar properties like identity, associativity, and all the other laws we are familiar with. And finally, we can use this free composition to describe the interaction between the two directions of a bidirectional program. And if you are interested in more details about this part, you can welcome to the presentation tomorrow at ICFP. And yeah, so I guess that's it. And thank you for listening.
Question?
Yeah.
Well, like one about the more general sort of use cases, like would we be applying like sort of rules and say more verification or root cause of programs?
Okay, so I guess the question is how this can be used in formal verification.
Yeah.
Okay, so it's actually a development of our work on effectful lenses, which is a specific type of bidirectional program. So we add effects to lenses, and we are actually using the round-trip relation to prove properties for those effectful lenses. So the intention of this development is that we can replace that reasoning with this free composition. So we can rebase all the theorems and all the theories, all the combinators, all the reasoning in our ICFP paper with this thing. So everything can be simplified and we get fewer axioms. So before that, we have 5 axioms, but now we have only 2 axioms for identity and composition. And all of the others can follow from that. So yes, indeed, it's for formal reasoning. Yes.
Okay, listeners. Okay, so I have one small question.
Yeah.
Maybe I'm wondering you could use this options for example, equational reasoning, but you have some applications of the opposed to read about the
So I'm not sure if I understand the questions, but yes, indeed, all these reasonings are using equational reasonings, right? So all right. Okay. Okay. So
some specific example in application. One of the some equation rules find to get answer. But the more specific equational
yeah. Okay. So I guess the thing is we want to separate the concerns, right? So we can have a generic combinator framework based on the general theory. So without knowing the concrete monads, we can still reason about them. That's for the abstract reasoning, which I have shown here. So we don't know the 2 monads M and N, but we can still do this reasoning and say that the first combinator and the sum combinator can be used for arbitrary effectful bidirectional programs. And it will still work and it should preserve all the properties. But yes, in terms of more specific effects, we can have some more specialized treatment. And definitely for specific effects, you will need specific effect-specific combinators, such as like we had a local combinator for the reader effect in our effectful lens framework. And you can imagine to have something similar to like a modified combinator for state and all the others that you can imagine. And actually, I have some backup slides for some other specific effects, like non-determinism, right? We can have different specifications for the interactions between two non-deterministic computations. And as long as these specifications satisfy the two axioms we require, then all the other things follow. And we can apply the whole theory to this specific situation.
Okay, yeah. Okay, so let's see. Okay, so the second talk is you want to speak of the second talk?
Hi.
Yeah.
Sure, let's just say it.
Microphone?
Okay. I'm very dumb. Hello. Oh. Sorry.
Okay, so the second talk is about the combination of a substructure type system and SSA. Yeah, please.
Hello. Hi, my name is Jad, and today I am going to talk about sound and complete refinement for substructural SSA. So, in particular, what we're going to do is we're going to give a denotational semantics for the SSA, or static single assignment intermediate representation, and then we are going to give a refinement theory for this, for SSA as well. Finally, we're going to prove that our refinement theory is sound and complete with respect to our denotational semantics. Or rather, we're going to sketch how all this is done in the paper since, you know, it's a lot. Let's be a little bit more precise here. So the first thing we're going to do is we're going to give an inductive representation of an SSA program, which here is the variable R. So ignore the gamma and L here. We're going to explain the gamma and leave the L implicit for the purposes of this talk. But the idea is that we have some kind of inductive type system on top of SSA programs. Once we've built our inductive type system on SSA programs, we can use this to inductively define a refinement relation on well-typed SSA programs. We're going to parameterize our refinement relations with a theory, R. And so think of this almost like a very discount version of an MLIR dialect, but the idea is that we can write down quite a bit of different kinds of information into this theory. So in particular, we can include equational information. So for example, the fact that a plus 0 is equal to a. But we can also include refinement information, and this refinement information can be effectful. So for example, here, if we have an undefined behavior effect and unreachable triggers UB, we could say that unreachable can be refined to any other program A. So this is very useful when we're modeling low-level languages, as you know we tend to be doing in SSA land, right? The other thing that we can have is, going back to effects, we could talk about commutativity between effects. So here we have the information that infinity, that is potentially going into an infinite loop, commutes with itself. So this is why, for example, something like Haskell could have two potentially non-terminating operations swap places. But again, since we have a refinement theory, our commutativity doesn't necessarily need to be two-sided. We can use Lipton's concepts of left movers and right movers. So, for example, undefined behavior is a right mover with respect to all effects, and therefore, in particular, infinite loops. This is reflected by the fact that unreachable followed by loop is the same as unreachable, which refines loop followed by unreachable, which is loop. But in general, we don't want infinite loops to refine into unreachable unless we're doing, something C style where infinite loops are UB. But we like our infinite loops to actually, not terminate instead of cause nasal movements. Those are unpleasant. So the last thing that we can encode in our refinement theory, and potentially the most interesting, is substructurality information. So in particular, our substructurality information is associated with effects. We want to talk about what multiplicity we can associate with an effect. And this multiplicity has a polarity. So these are a bunch of fancy words, so let me give a concrete example. In the positive polarity, that is, we are refining, right? Undefined behavior has unrestricted multiplicity. So all this is saying is that if a variable is used twice and its expression, has potential undefined behavior, then we could duplicate that variable. So, potential UB once is the same as potential UB twice. But on the other hand, if a variable is used no times in the expression, here we just have the null expression, then we could just remove potential UB. It's always safe to eliminate potential UB. On the other hand, for the negative polarity, we have that our multiplicity is irrelevant. So what that means is that it's still safe to duplicate, as we said before, but we can't eliminate. And the reason is very simple. If I have a program which does nothing, it would be quite dangerous to randomly stick UB on the front. So our multiplicity information for effects is directed. Don't worry, I'll give some clearer examples later. There's just a high-level overview. So now, once we have this refinement relation, going back to our original typing derivation from both sides, obviously this satisfies reflexivity, and if R refines R prime, then both sides are well formed. So all the usual syntactic theorems. But we're going to take our derivations here, and we're going to assign them a denotational, and in particular, a categorical semantics. However, we're going to take one step further, and we're actually going to assign our semantics in a poset enriched category. So all that means is that our Hom sets are equipped with a partial order. And when we do this, we get a nice and, slick way of representing soundness and completeness. Soundness just means that if R refines R prime, then for every category modeling the theory R, the denotation of R is less than or equal to the denotation of R prime. Whereas completeness says that if all categories modeling R have that property at the bottom, namely that the denotation of R is less than or equal to the denotation of R prime, then it will in fact be derivable that R refines R prime. So this is an interesting property because it shows that our refinement system is in some sense the most powerful refinement system. Anything which can't be derived in a refinement system has at least one model in which this is not true. So this is our high-level kind of contribution. We also provide some cool models to show that this is not just an abstract symbol shuffling game. And in particular, we talk about some interesting side effects, such as release, acquire, weak memory, sequentially consistent concurrency, which is, simpler, but also nice, undefined behavior, and all kinds of other fun stuff. We formalize significant portions of this in Lean, though the whole formalization is not done yet, primarily because I discovered locally nameless. I'm in the process of redoing it because I can't help myself. And we also introduce another language, lambda item, which it turns out is very important for actually getting this mess to work. So that's a slightly more low-level kind of description of what we do in the paper, but a good portion of this audience is probably still lost, and that's because I still haven't answered a particularly important question, which is, of course, what is SSA? So while describing this, I'm going to talk about what SSA is. Consider the following highly complex imperative program written in everyone's favorite imperative language, while. I really don't understand why anyone invented any others. So this program prints the numbers from 0 to n. Not inclusive, of course, as is, right in prior, right? So while is an excellent language. People have been teaching semantics courses about it for the past 10,000 years or so, but we're imagining it's a more complicated imperative language that is hard to do semantics on, and moreover, this is structured control flow. It's not, we don't have a while CPU. I guess WebAssembly counts as a while CPU, maybe, but that has too many features. We want an intermediate representation. So, the most common intermediate representation is just literally doing, taking this and breaking it down into basic blocks. So boink, and these are the basic blocks of our program. So what is a basic block? A basic block is a series of instructions. So that printx is an instruction, and every assignment is an instruction. If we really want to be uniform, we can treat printx as an assignment to a temporary variable we don't use. And then each instruction is followed by a terminator, which tells us where we jump to next. That can be a conditional branch, which jumps to either A or B, or an unconditional branch, which just jumps somewhere, right? And these basic blocks have labels. So all we do is we take this and we kind of lower it down into unstructured control flow in a mechanical way. This is called the readdress code, or RTL. Now, this intermediate representation is great. Lots of compilers use it, but the problem is if you can't do algebra. So if I want to reason about the value of x, right, we can label all the definitions of x pretty easily. So here you have x0, x2, leaving a gap for x1, but I don't know what value the x takes in, the print statement or in the addition or in the if statement. And the reason I can't just, pick a label here is because it's either going to be x0 if we're coming from the entry block, or it's going to be x2 if we're coming from body. So SSA basically says, okay, write that down. Now there's two ways to do that. The first is to have a phi instruction whose value changes depending on where we come from in control flow. And the second is to annotate our basic blocks with parameters and then give the value of those parameters at the call site. It turns out these are exactly isomorphic. It just basically where you give the annotations. If you give them at the call site, then you get basic blocks with arguments. If you give them at the callee, then you get phi nodes, and these are exactly isomorphic. It's a syntactic isomorphism. So we're going to use basic blocks with arguments. And the reason why we're going to use basic blocks with arguments is because I'm sitting in a room full of functional programmers. So everyone here is just like, may God preserve us from imperative programs. These are just simple, tail recursive functions. Why don't you just write these as tail recursive functions? And that is the idea of Appel's wonderful paper, SSA is Functional Programming, which is where all this categorical semantics nonsense starts. So how do we convert this to an actual well-scoped functional program? Well, first off, we need to ask ourselves how this mess is scoped. So let's go do that, right? If we look at the data structure here, the data structure here looks like we have a bunch of basic blocks, which are vectors of operations. Each one defines a variable v, followed by a terminator. And then we have this flat control flow graph that just has the one entry block and then an ordered, or rather unordered map of labels and basic blocks. So the order of our basic block doesn't matter here, which is nice, but the problem is this is not a nice thing to do induction on. It's a really unpleasant thing to define a type theory on. I did that once in 10,000 lines of lean, and I'm never going to get those months of my life back. So let's not do that again. Let's look at our control flow graph here. So we see that if we want to get here to the loop area, then we need to go through the entry block. And so therefore, any definitions in the entry block are visible in the loop area. On the other hand, we can get to the loop area without going through the body area, namely, the first time. So any definitions in the body area should probably not be visible in the loop area. Similarly, we can get past the body area without ever touching it. So definitions in the body area should not be visible past the end if there's anything past the end. So if we look at our control flow graph, what I've just described to you is a relation which is called dominance. If we draw dominance here, it looks like these red arrows. Now, what is important to note about dominance is that we have this structure called the dominator tree. Namely, it turns out that, ignoring unreachable blocks, because those don't matter and cause suffering, we have the interesting property that there is precisely one block which dominates you and jumps directly to you. That's called your immediate dominator. So this actually gives our graph the structure of a tree. And the nice thing about trees is that we can do induction on trees. So that tells us how to scope our variables. We scope our variables based on the dominator tree. And this is the core idea of SSA's functional programming. But this doesn't just tell us how to scope our variables. It also tells us how to scope our basic blocks or our functions here. So in particular, if we look at our dominator tree here, I'm now going to swap the contrast here. So, the CFG goes gray and there's our dominator tree, right? If we look at that, right, we see that if I added, some extra edges from, say, the body to the rest of the function or the rest of the function to the body, that would not change the dominator tree. Similarly, if I added a thing that jumps from the rest of the function back to the loop, that wouldn't change the dominator tree either, right? Because we still need to go through loop to get to the rest of the function. But on the other hand, if I added a jump straight from the entry node to the rest of the function, that would change the dominator tree, since now there's a new way to get somewhere. So the invariant here is there can't be any new ways to get somewhere. Because if there is a new way to get somewhere, then the dominator tree will be broken. Just to make this more clear, let's say I added another node over here. That doesn't change the rest of the dominator tree. And now, if I added a function from that node to loop, still doesn't change the dominator tree. Everything is good because there's no new way to get through loop without going through entry. So, the relation is preserved. But again, if I jump from there straight to the end, same thing. There's a new way to get to the end of the function, and dominator tree is broken. So the intuition here is that the subtree rooted at a given point in the dominator tree is obscured. The dominator tree tells us what is visible. We can't jump into the subtree without breaking the dominator tree. Same thing again. The subtree down there is obscured. So if we think of it this way in terms of scoping, what are we doing? We're inserting these little where blocks here. Let's reorient that so we can see that more clearly, so that we can only, so that when we enter a scope, when we enter a subtree, any basic blocks in that subtree are only visible from within that subtree. That ensures dominance. And now our variables are just lexically scoped immutable let bindings. So this tells us that SSA is precisely the same thing as, just with a little bit of let floating, these mutually recursive first-order functional programs. And so therefore, this is just a syntactic isomorphism. You can go from one to the other. The dominator tree can be computed in nearly linear time. So now we can try to build our type theory on this inductive representation. And that's great, except that the refinement relation we're going to get is really complicated. It fills up pages and pages and pages of text. And I don't want to explain that refinement relation, considering I've spent 12 minutes talking already. Oh, also, one last thing is we're going to replace those if statements with cases. So usually cases desugar down to if statements and fallible projections. So that is, A plus B can be projected to A and it's undefined behavior if it's B. That's, for example, how Rust does it. But we want to work with cases because we want to be able to support higher level languages like ML, where we don't want to be sprinkling in undefined behavior unnecessarily. So that's just a quick aside. So the idea is that we want to switch our data structure, right, to a slightly nicer data structure, where the idea is that, so our scope here has the ops, the terminator, and the children that we can jump to. And the idea is those children can jump to each other, and you can jump to any of your ancestors and your ancestors' siblings, but what you can't jump to is any of your ancestors' children. So anyway, this is what we have so far. Is we have while, and then while compiles down to RTL, and RTL compiles down to SSA. That's our adventure so far. Now, it turns out that RTL and SSA are in fact isomorphic, because you could just take those SSA arguments and turn them into extra variables. But while and RTL are actually isomorphic by the Bohm-Jacopini theorem, right? So what this really is we have an axis here of structured to unstructured. And again, I don't want to write down the refinement theory for SSA. I've done this. It's horrible. I don't want to do it again, especially not in this presentation. So we want something over here that is structured, but like SSA. But what's the difference between RTL and SSA, right? Because we don't just want to work with while. If we look at RTL, the variables are mutable. If we look at while, the variables are mutable. But if we look at SSA, the variables are immutable. So what's the immutable thing that has structured control flow? Well, why don't we just come up with an expression language for structured control flow? We're going to call it lambda iter. if such an expression language is isomorphic to SSA, which hint it will be. So notice we can see how to compile this to SSA pretty simply. Once we give it, it will be obvious. And then compiling SSA back to the expression language is a complicated transformation that is described and proved semantics preserving in the paper. So we're not going to go over that. But the idea is if we have an isomorphism here, we actually have a nice little commutative square of isomorphisms. And I love commutative squares of isomorphisms. Of course, everything will be up to semantics. So yeah, what's this lambda iter? What's this iteration expression language? So, well, it's literally just ye old expression language with iteration. So in particular, we're going to have expressions of type A. Context are going to be a bunch of variables that have types. You know, this is pretty standard, I hope. And similarly, we're going to have a refinement relation on it. And just like before, we're going to parameterize our refinement relation by a theory R. And just like before, we're going to give things a denotational semantics, poset enriched to so notice that's going to be a morphism from the denotation of gamma to the denotation of A, where the denotation of gamma is just going to be the tensor product of the denotations of all its variables, right? We're going to poset enrich that, soundness and completeness, and not here, but later on, if we look at our SSA transformation, we're going to show that that holds if and only if the transformation to SSA holds. And likewise, we're going to have a compilation from SSA back to expressions that is basically going to be the Bohm-Jacopini transform, but lowered down to the SSA world. So going back to our expression language. Well, so our expression language should obviously have variables. So let's add those in. Similarly, it seems useful to have function applications. So let's add those in too. Those are our operations. Very exotic so far, right? We also have a very, very powerful and exotic operator known as the let binding. This implements sequencing. Okay, so far so good. Now for our first weird feature is that we're going to add an effect system to keep track of all our effects. But this is literally the simplest possible effect system in that all our instructions F are tagged with effects. Effects form a partial order. And we're just going to find out basically what is the supremum of all the effects that appear in a, they form a semilattice. We want to find the supremum of all the effects that appear in an expression. So this is just, simplest possible effect system possible. Now, when I said that our sequencing operator was exotic, I meant it was actually exotic in the sense, not in the sense of how it works, but in the sense of the rewrite rules that it can do. See, the usual rewrite rule for a sequencing operator is substitution, but A can be effectful. So general substitution is always well typed, but just because it's well typed does not mean that it has the same semantics. In particular, we are discussing refinements. So we should ask when the substitution is a refinement of the let binding, or the other way around, when the let binding is a refinement of the substitution. What we're asking is whether A can be pushed over and through B, or whether B can be pushed, or whether A can be pulled out of A and merged back together. So notice there's two questions there. The first question is what is the effect of A, and what is the effect of B? Can we take the effect of A, epsilon, and push it over the effect of B, eta, or vice versa? Can we pull it backwards over the eta? That's our first question. Second question is how is X used in B? So how often does X appear in B? That's going to be our quantity Q. Now our quantity is going to take values in this fun lattice. It's either used once, linearly, or it's unrestricted, but we're also going to have the option to be used in an affine way or a relevant way. So what does that mean? Well, consider the following case statement. In branch 1, X is used once, but in branch 2, X is used 0 times. So therefore, X in the case statement as a whole is used affinely, since it's used either 0 or 1 times. Likewise, over here, X is used 1 time there, but 2 times there. So it's used relevantly because it's used 1 or 2 times, but it's never used 0 times. And finally, we're going to add one more thing to make things a semilattice, which is where X is used 0 times, we give a distinguished value. So it's just a very, very simple kind of inductive analysis to find out what the quantity of every variable is. Again, we can compute this very, very fast. Once we know that, we want to add 2 conditions to our judgment. So let's start talking about where let, right, is a where let is refined by the substitution. So we're going to talk about the forward direction first. So to do that, the first thing that we need is we need that epsilon is a right mover with respect to eta. So in other words, that we could take epsilon and push it forwards over eta. And the second is that whatever quantity X is used in, that's something that we can duplicate or fuse epsilon, appropriately with the polarity that we had before. And then we have this. So in this example, maybe A is undefined behavior and X is used arbitrarily, and this will hold. That works. Or maybe A is non-determinism. If A is non-determinism, well, we're allowed to eliminate non-determinism, so X can be used affinely. But on the other hand, we're not allowed to duplicate non-determinism. Non-det is not the same as let X equals non-det XX. So therefore, that would fail. And if we want to do this backwards, we literally just flip that. We go from positive polarity to negative polarity, and everything still works out. That's going to be our directed substitution rule, and that is the second weirdest rule in this entire type theory. So again, it's not that weird. The rest of the rules are profoundly obvious, and explaining them also tells you what our semantics is, because it turns out we're almost directly giving the underlying semantics by our rules, where we're basically giving the free theory. So in particular, we will introduce pairs, we will introduce units, and we will introduce pair destructuring. We'll also introduce a beta operation on pairs, which basically says that in the arbitrary case, the pair let x, y, a, b, c just becomes two let bindings. In particular, we execute A first and then execute B. So pairs are always executed left to right. This, combined with the appropriate eta rule and a few weird kind of shuffle rules, gives our category the structure of a fried category. So what is a fried category? A fried category is a premonoidal category. Now, what is a premonoidal category? It's like a monoidal category, except the morphisms don't necessarily slide over each other. So all that means is that if I have two variables, let's say x and y are both of type nat, and we print x, and then we print y, so those two things are in parallel, but that's not the same as printing y and then printing x. So we don't have the sliding rule, but all the other rules of a monoidal category are still in place. And yet this premonoidal category actually has a Cartesian subcategory, right? It is a wide subcategory, which means it has all the objects, all the types, all our types can be freely duplicated, but it doesn't have all the morphisms. And this Cartesian subcategory is particularly going to be, right, is particularly going to be formed by the morphisms which have bottom effect, or in this case, the terms which have bottom effect, right? So this gives us the structure of a fried. But we don't just want a fried category, we want to be able to deal with control flow. So let's begin with, a cyclic structured control flow. So we're going to add in injections and abort, and we're going to add in case statements. And we do that, and ta-da, with the appropriate obvious rules, we get coproducts. But there's something more interesting here, which is that we can thread in these gammas into a case statement. So in particular, a gamma can, so variables gamma appear in both branches of the case statement. And if we fiddle through all the semantics, what we're saying is not only that our category has a coproduct, but that our coproduct is distributive with respect to our premonoidal structure. So all that means is that there's an isomorphism from A tensor B plus C to A tensor B plus A tensor C. And that's just the same as this rule here. So far, everything here has been utterly standard. There's literally only one weird part to this calculus, and that is, of course, our rule for iteration. So bear with me here. Our rule for iteration takes an initial value A. We need to provide an initial value since we actually pass in the state explicitly, right? And then given the current value, which of course starts out at the initial value, that's why it's called initial, right? We execute a body. And the body is going to return a coproduct. In particular, it's either going to return a B, in which case we're done, and we return that B. That's our B there. Or it's going to return an A, and we execute for another loop. So notice, this is none other than a while statement. Actually, it's a do while, if we want to be very precise here. All this is a do while block. If anyone knows what the RVSDG is, we might call this a theta node. All this is a do while block, but we thread through the state explicitly. So it's immutable rather than mutable. And our effect system is exactly the same as before, except we additionally have the constraint that whatever effect we assign an iteration statement must contain non-termination. So we just assume that there's a distinguished non-termination effect here. It's a little bit more subtle in the paper, but that's good enough. Great. And once we've done that, that's a typo. We want to actually give a reduction rule for our resulting thing here. And our reduction rule is going to look a lot like the fixed point rule over here. So the fixed point rule over here just says that, this is one of the rules of what's called an LGOT category. So an LGOT category, specifically a strong LGOT category, is just one of these distributive Fried categories equipped with an iteration operator, which is a trace in the coproduct that satisfies this and other equations. So in particular, all this is saying is that F looped in on itself is the same as, executing F. And if we're in the terminating branch, go. If we're in the continue branch, then, that goes into the loop. So it's exactly what we just said before, but translated as a control flow diagram. And if we take this fixed point rule, we can translate it almost directly into a typing rule. So all this says is that we can just unfold the first iteration on the front of an iter. And in particular, the other axioms, such as codiagonal, which looks like that, naturality, which just says that, anything immediately before a break, we could just pull after that break. And codiagonal and naturality are both satisfied. And finally, we have a really weird axiom, which is uniformity. So uniformity says that if H followed by F is the same as G followed by H, or rather, sorry, refines G followed by H with H in the continue branch, then H followed by the iterative F is the same as the iterative G. However, we have to have the condition that the effect of H is a right mover with respect to the effect of F. Otherwise, this will lead to subtle inconsistencies. Now, the intuition behind this is not very complicated. All we're saying is that if we take our iterative F and unfold it into the appropriate infinite tree, we could just apply that single rewrite infinitely many times. So notice, to do this finitely many times, we don't actually need the commutativity condition. But we do need the commutativity condition to do this infinitely many times. That's just how this works. We might be able to weaken it to just commuting with infinity, but I haven't tried yet. And I'm not going to go over the typing rule since we're running out of time. But what this does is that once we prove this semantic sound and complete, we can also give a semantics for SSA in the obvious way by just taking our SSA program's control flow graphs and interpreting those as the semantics. Again, I don't have time to go over that. And we can prove not only that all the arrows up there are semantics preserving, but also that the arrows down into the semantics, so in the case of lambda-id or LGOT categories, so that's an if and only if by soundness and completeness. LGOT categories are the same as data flow string diagrams over the tensor product and control flow string diagrams over the coproduct. And the Bohm-Jacopini theorem says you only need to nest these one deep, but ask me about that later if you really want to know. And so that's another if and only if. And then that gives us an if and only if with SSA, combined with the fact that, we do have this denotational semantics for SSA. So what we've done is we've actually kind of created a semantic ladder, where the bottom layer of the ladder, it looks like semantics, but what it really is actually a point-free representation of the semantics of SSA programs. And now, what's cool about the semantic ladder is you can use it to reason about optimizations, analyses, but most importantly, memory models and side effects at whatever rung of the ladder is convenient. So in particular, it turns out to be, much more simple to do, say, weak memory over an LGOT category land, and through the existence of the ladder, you know that valid SSA optimizations like loop unrolling or distributing things across if statements will work as long as you validate the core rewrites inside your theory. So you might have a rewrite like stuttering, which says that x equals 2 can be refined to just x equals 2. So you just have, that duplicated right goes into 1. And if you just prove that rewrite sound, this theory says that any SSA optimization that uses that rewrite alone is also sound. And yeah. That's what we've done. Sound and complete refinement for SSA through this lambda-id language and, building up this ladder. Thanks for listening.
Thank you very much. So you might know there's a framework in the compiler community called MLIR.
Yes.
There's a flavor of SSA that I'm going to call hierarchical SSA.
Yes.
That allows basically to have control graphs nested inside of
Yes.
operations. So how would you model this in your?
Well, that's excellent. I'm actually working on a model of hierarchical SSA. And so the thing is if you look at MLIR, it's actually a bit more subtle than hierarchical SSA because you have multiple kinds of regions. You have SSA CFG regions, which can be nested. Then you also have graph regions and other nonsense. But let's assume that we only allow what you said, hierarchical SSA, so just nested SSA CFG regions. If you do that, then your operation, so right now we have the simplicity of only basically dealing with binary operations and passing in, a tensor product of things. You can't do that anymore because you want to pass in n regions and you don't want to go higher order, so you actually need n-array operations. Once you do that, the semantics of your operations becomes, and I'm still conjecturing this because I'm working on it, basically a function that takes in one morphism per region parameter and then takes in your operation parameters unchanged. And the only real constraint you have is that this function is continuous with respect to those morphism parameters. So all that means is that, if morphism F refines morphism G, then op F refines op G with, all the other parameters unchanged. And I conjecture that if you have this, you can have a similar kind of free refinement theory for hierarchical SSA, and you could generalize your theory appropriately to do interesting things like pulling operations in and out of hierarchical region. And I'm particularly interested in this because I've started working on weak memory models, as you see. And one cool thing about weak memory models, if you look at like Brooks-style trace monads, is that you can actually talk about the laws of parallelism by having, a parallel composition operator, which naively is a higher order operator. But if you do this, you could have a parallel composition SSA operator and talk about, okay, what are the laws of parallelism here? What's the free model of parallelism? And that's my current future direction of research that hopefully I can jam into the last chapter of my thesis. We'll see.
So for example, in the theorems.
Yeah.
And consider
That's right. Hello.
If you don't know it.
Right, how's it going? Great.
It's the chip.
Very nice. Okay.
No stations.
Yeah, I think that's. Yeah.
Which you tend to be marked. It's not just a second.
This one that you want to learn, you got the when, how, from.
Yes.
Okay. You okay?
Yeah, I can.
Okay, so this is the last talk of the workshop. It's 1 hour talk. So the presenter is when, how, from.
Thank you. Yeah, so I'm going to talk about rules and capabilities at modal effects. This is John who work with simultaneously sitting there. And yeah, so I'll start with some backgrounds on effects and effect types. Effects are the way that programs interact with their environment. And there are many examples like I/O concurrency exceptions. And effect types is a type system feature that statically tracks the use of effects. So that we can know that by looking at the type, which effects a function might perform, and if it is safe, if we just run the function under a global pure environment. And I think in the past 10 to 20 years, there have been many different proposals on different effect systems. And many of these recent proposals are based on either rule types or capabilities. So let's start with rule-based effect systems. So here we are focusing on system F epsilon, which is a co-calculus of the Coca research language. The key idea of the rule-based effect system of Coca is to annotate each function arrow with a rule of effects. So, so instead of just have a function arrow from A to B, we have an actual annotation E, which means that this function might perform effects E when it is applied. Here is one example. Supposing we have a global operation yield, which takes an integer and yields it, returns unit. And we can write a function which takes a parameter x and yields this parameter x by invoking the yield operation. So the type for this function is from int to unit and might perform the yield operation. So here's the typing derivation of it. So the bottom conclusion is this function, and we first using the abstraction rule to introduce the parameter x to the context gamma. And then the function body is an operation invocation, which might perform the yield operation as being tracked here. And then we use the T-do rule, which is for operation invocation. Supposing that we have an operation yield and make sure that the argument x indeed have type x, indeed have type int. So as we can see here, all functions in a rule-based effect system are pure, because when we create a function, so that when we create a function, we need to capture all the effects might be performed by this function in the function type. And one feature that is typically required by rule-based effect systems is parametric effect polymorphism. So for example, here we have a higher order apply function, which takes an argument function f from int to unit and another argument x and applies f to x. Assuming that the argument function f performs some effects E, so the result function should also perform E because the result function invokes the argument f. And in order to have a modular version of this function, which could be used with any effectful argument, we need to use effect polymorphism. So we have this big lambda to introduce an effect variable epsilon, and use epsilon to replace the big E everywhere. And when we apply this function, we instantiate epsilon with the effect type we want. So that's rule-based effect systems. It is, I think, pretty standard. If you are familiar with some existing works or graded models, then it should be familiar to you. And the capability-based effect types are relatively new. So here we are focusing on system C, which is the co-calculus of effect. I think I saw Jonathan here, the order of effects. And the key idea is to treat effects as capabilities provided by the context. So here we have this double arrow, which is a block, essentially a second-class function in effect, and it takes a list of arguments, a list of value arguments of type A, and another list of other block arguments, f of type T, and returns a value of type B. Yeah. Yeah, so as we have seen, system C distinguishes between first-class values and second-class blocks. And here is a concrete example. We again have the apply function. It is an anchored version of the apply function, which takes x of type int, f, a block of type int to unit, and applies f to x in the block body. So f here is a capability that is bound by this block construction, and it can be used in the block body. It also appears in the type as we see here. We have the name of f appearing in the type of this block. So blocks are second class in the sense that they must be fully applied and cannot be passed and stored as values. So one advantage of requiring blocks to be second class is that we don't have to track which capabilities are used in the types every time. And blocks can just use any capabilities from the context. So for example, in this function, instead of calling f here, we are calling a capability y from the context. But we do not need to track the capability y in the type of this block because blocks are second class, and the lexical scoping guarantees that y will never escape from the scope that it should be in. And this is the main advantage of capability-based effect systems. Yeah, and in order to write a current version of the apply function, we have box in system C, which turns blocks into first-class values. So for example, here we have app prime, which is a current version of the previous app block. It first takes an argument, a block argument f from int to unit, and returns another block from x to f of x, which is boxed. So it is the first class value, and we can return it from a block. And in its type, we have this. And in its type, we have this at f, which means that the block from int to unit captures the capability f. So whenever we want to use the return value of this return value of the app prime C again, we need to make sure that the capability f is within the context. Yeah, so I think these are the two probably the most popular kinds of effect systems currently. And there have been some work trying to understand and unify those different kinds of effect systems in the literature. Oga et al. Proposed a framework to compare different role-based effect systems. But they left capability-based ones for future work. And it is now obvious how to systematically translate between a role-based effect system like system F epsilon and a capability-based ones as system C. Because if you look at the type or the function types in both systems here, if we want to go from system epsilon, if we want to go from system F epsilon to system C, it is not obvious how we should systematically translate the effect rotation into something in system C. And if we want to go the other direction, it is not obvious how we should translate these type level capabilities into corresponding types in system epsilon. And we claim the main problem of translating between role-based and capability-based effect systems is that effect tracking is deeply entangled with other type system features. As we see here, a function type, it's not merely a function type. It also does some non-trivial, it also performs some non-trivial rules in tracking effects. And so this kind of situation or entanglement is reminiscent of the translations between call by value and call by name. So if we want to directly translate between call by value and call by name, it is non-trivial. It typically requires some like continuation parsing translation or some global manipulation, because when to suspend and force computations is entangled with functions. And the callback push value smoothly subsumes both by decoupling sunking and forcing from function abstraction and function application. So our observation is, why don't we do this for effect tracking? Why don't we decouple effect tracking from function types? And so we propose modal effect types, which is a recent effect system based on multimodal type theory and inspired by the languages Frank and Effect. I'm going to give a talk on modal effect types this Saturday at Uppsala, which will be a different story from what I told today, but what I'm telling today, but yeah. Yeah, so one of the key ideas of MAT is to decouple effect tracking from standard type and term constructs via modalities. And for the purpose of this talk, you can think of modalities as some special type constructors with specific meanings, which I'll show later. So, and we rely on the decoupling to have the flexibility to simulate the effect tracking in different systems. Yeah, and we propose a framework, MATX. I'll explain what is X later. So, okay, so now I'll introduce some details of modal effect types. The most important concept of modal effect types is effect context, which is part of the typing judgment, which tracks which effects might be performed by the term. So for example, here we have the function lambda x do yield x, which is a function that invokes the yield operation. And the typing judgment tracks that this function performs the yield operation. It is worth noting that the type of this function is just int2 unit. There's no effect notation, and this at yield is part of the typing judgment instead of part of the type. The key idea behind the effect context is that the whole term shares the same ambient effect context. So for example, if we apply the application function to the previous function,
So something's gone wrong.
Mic is off.
Oh, it's oh. So.
Any better yet to respond?
Oh, it works. Okay, good. Yeah. So the key idea of effect context is that the whole term shares the same ambient effect context. So for this function application, for this partial function application, every part of this term has the same effect context yield. So we can use the yield operation in this argument lambda x to yield x, and we can also pass the function to the add an argument to the first apply function. So
I think change that battery.
yes. Yeah, so even though we have int to unit as the type annotation of the argument f, we can still apply an effectful function that performs yield to it because the ambient effect context because the ambient effect context allows us to use the yield operation. And we have a natural notion of sub-effecting here. So for the function that only performs yield, we can of course put it under an effect context with both yield and ask. Yeah. So after having effect context, we can have modalities which characterizes the changing of effect contexts. An absolute modality has the form square brackets E, which changes the ambient effect context to E. So if we apply it to some other effect context F, we'll get E. And here is an example of introducing the absolute modality. We have this mode syntax for introducing a modality, which introduces this modality to the type of the conclusion, also a log in the context. Yeah, there are some problems with my type compiler. Yeah, so for the premise, its ambient effect context is it's not f anymore, but yield, which is specified by this absolute modality. And we also have a relative modality written using angle brackets. It does not completely change the effect context, but adds some new effects to the context. So applying angle brackets E to F gives you E and F. So the same example here, but changing from square brackets yield to angle brackets yield. For the conclusion, the effect context is ask, and for the premise, we not only have ask, but also yield, which is introduced by the relative modality. So these logs introduced by the modalities are used to control which variable we can use. And I would say that the essence of effect tracking is to determine which variables we can use and which variable we can't. So here is an example of an invalid judgment. We are using some function f at the context ask within mode square brackets yield. This is not safe because f might perform the operation ask, but within the scope of this mode syntax, we should only perform the operation yield. And it is rejected by the type system because its premise does not hold. For the typing premise of the function, we have a lock in the context annotated with the square brackets yield, which prevents the function f to be used. Because f is from a different context than matrix ask, but now we only have yield here. In order to make it well-typed, we need to annotate the variable binding of f with some modality, for example, the empty absolute modality, which means that f itself is actually a pure function because it is from a context where there is no effects. And such a binding with a modality annotation is introduced by modality elimination. For example, if we have some value v of modal type int to unit with the modality empty square bracket, you can use net mode empty square bracket to eliminate the modality of v in order to have an annotation on f and documents the information that the function bound to f is from some environment with no effects, so it is a pure function. We can use it freely. Yes, and by default, if there's no annotation, it is the empty relative modality because it works as the identity on effect contexts. Yeah, and the type system decides which variables can be used after which locks using a modality transformation relation. Yeah, so for example, for the uses of f here, we can use f with annotation empty square after the log with annotation square bracket yield. If we have the transformation relation from the empty square bracket to square bracket yield. And intuitively, this kind of transformations tells us which variable can be used after which log. Here are some more examples. So if we have something that may only use E, then we can use it at some other context F as long as E is smaller than F. And if we have something that use no effects, then it is actually a pure term. We can use it anywhere. So this relation holds for any mu. And if we have something with the empty angle bracket, which means that it is a term that depends on the current ambient effect context. So we cannot use it under some specific effect context because at this stage, we don't know what is present at the ambient effect context that the term is defined. Yeah, and another question is, what if there are multiple nodes? So if we have some f with annotation mu, there are 3 nodes, v1, v2, and nu1, nu2, nu3, we have this composition relation to compose these modalities, and then to check that mu can be transformed to the composition of nu1, nu2, and nu3. So the composition of modalities is defined very intuitively. It reads from left to right. So for the first one, if we have some arbitrary mu followed by the square bracket E, then because an absolute modality fully specifies the effect context, it has to be square bracket E. And for the second one, if we start with some square bracket E and then extend it by some D, then it is equivalent to just have square bracket D comma E. And for the third one, if we consequentially extend some context with D1 first and then D2, it is equivalent to just extend the context with D2 comma D1. Yeah. And for encodings, we also introduce effect theories because different effect systems organize the structures of their effects as different structures like simple rules, scoped rules, set multisets. But how do they but how do they organize structures is orthogonal to our main motivation of simulating their effect mechanism. So we introduce, so we parameterize the calculus with an effect theory following the work on abstracting rho times and abstracting effect times. So the effect theory X defines the structures of effect actions. So for example, we have this RSCP for scoped rules, which is the one used by system epsilon, and S for size, which is the one used by system C. And we use MAT RSCP and MAT S to encode systems epsilon and C individually.
Well,
yeah.
It might be worth pointing out this point that we should pick a different name for effect series. It's a terrible name for what this thing is. It has nothing to do with algebraic effect theory, so.
Yeah, this is a terrible choice of names. We'll consider differently and suggestion will come. Yeah. Okay, now we can go to encodings. It is super easy to encode rho-based effect systems because that a function from A to B with effect notation E is a function. It's a function that might perform E and only performs E. This is very similar to what absolute modality does. So we just translate the effect annotation E as an absolute modality, which fully specifies what are the effects that might be performed by this function. And here are some examples for the first function we have seen with lambda x to yield x. We translate the type from int to unit with yield to the function type int to unit with an absolute modality which specifies yield. And the term translation correspondingly has a modality introduction. And for the effect polymorphic application function, it has 3 function arrows. So we have 3 absolute modalities in the translation. This one is for the middle arrow, and these 2 are for the first and the second and the third arrows. And this quantifier of effect variable is kept by this translation. And the term translation is similar, but we insert some introduction and elimination for these modalities. Yeah, and to encode the capability-based effect system is more involved because a block construction does several different things in system C. So these 3 programs are variations of the application function that we have, of the application blocks that we have seen before. And from them, we can see that a block construction at least does these 3 things. First, they all bind both term level and type level capability F, which could be used in terms and could also be used in types. Yes, and for the block body, we can invoke the capability F as in the first example. And also we can use any capability from the context, as in the third example where we invoke the Y capability from the context. So the key idea of the translation of system C is to simulate these three different things. So for the first one, we have to introduce a type level variable in order to allow the capability F to appear in types. So we introduce a quantifier of F star here, and for the block argument, we box it with the absolute modality of F star to make sure that whenever we want to use this argument, F star must be present. And for 2 and 3, we use a relative modality of F star to wrap the whole function, so that first it makes sure we can use the capability F in the block body, because this relative modality extends the ambient context with F star. And second, we can still use any other capabilities from the context, because a relative modality still allows us to use those effects from the context. And here is the term translation of this function, which mostly mimics translation of types with some explicit introduction of variables, of the effect variable, the modality, and the elimination of modality. Yeah, and so system C also have these boxes which which allows us to turn blocks into first-class values, and we can just encode them with an absolute modality. Because in system C, when we box something, we need to fully specify which capabilities are used in the block, with exactly what absolute modalities do. Yeah, so here, for the result block into unit at F, it is encoded as a function from int to unit with an absolute modality of F star. And for the terms, we encode this box to an introduction of the absolute modality of F star. And yes, so now we have seen how functions in system F epsilon and system C are encoded. But by encoding them into an uniform target, we can easily compare them. So I think there are main two obvious observations here. The first is that when encoding system F epsilon, every function is translated to a function with an absolute modality, but every block in system C is translated to a function with a relative modality. So it reveals the difference that in system F epsilon, when we have a function type, we must fully specify which effects are used. But in system C, we do not need to do that. And every block can use whatever in the context without claiming it in the type. And another difference is that for the encoding of system epsilon, F epsilon, we only have a quantifier in the target if we have a quantifier in the source. But for the encoding of system C, each function is encoded to a polymorphic function type with some quantifiers. So I think this somehow explains the observation that when programming with rule-based effect systems, people usually need to use effect variables everywhere. But when programming with capability-based effect systems, we do not need to use explicit effect polymorphism in most of the cases because every block somehow does the job of effect polymorphism.
You got us.
Oh yeah, okay. I think I still have plenty of time, so I'll keep going. Yeah. So
If people want to ask questions.
oh yeah.
You ask. You ask later, but.
As you mentioned, the multimodal type theory.
Mm-hmm.
So the your effect theory of the that effect and the whole actually of the
Yes, they form a double category.
and another thing about this problem. So in system epsilon, you don't need to have any kind of function or anything about effects in the system. But you if some specific type, for example, for app translated in the key translated in the embedding bracket with the that star it requires. So like why do you need the implementation of like what's the difference in terms of use? If we translate the system as epsilon, then we need to use directly E or epsilon. System app we need to use the argument with pi. But like it seems a bit weird when we have just one system for effect. Even like one encoding the parse type and one encoding the reverse type, but they are in the same system. Why don't we identification perfect?
Oh, because I think system F epsilon is relatively more simple, in the sense that, the parameters of its functions, do not do any actual things, but just introduce a term level parameter. But in system C, you can kind of think of block system C as some lightweight form of dependent types. So the parameter names cannot only appear in terms, but also in types. And in order to simulate the ability of having parameter names in types, we have to introduce some type level variables to stand for these parameter names.
I mean, also when we actually use the term, how do you use E in the system epsilon, like encoding of system epsilon, and how do you use the effect app in the encoding of system? I don't see effect. I don't see the effect E in the encoding of system. But like if we are in the same type system that I don't see how we can one page on one side and one page on yeah.
Oh, wait, I didn't get the question, but E is used here, so what do you mean by?
Yeah,
is
there. Is there. We don't have type notations or like we don't have any types related to the E and in the.
Oh, I see what you mean, but if you look at the source, there is also E here, and A and B. Well,
I mean, I understand the difference between system epsilon and system C because I mean they are two different systems, but we encode those two things into a single system. Then like we probably need to do it. We definitely need some unified way to deal with the effect.
So I think probably this example can answer your questions. So here in the type we have yield, And in the term of this type, we use do yield. So the yield is used here, right? And in its translation, well, we still have do yield here. So this is where the effect notations are used. What's the type?
How do you know the type of?
So the global signature.
Yeah, right. Okay.
There should be some global signature even like before. But in the encoding, the other encoding, we don't need that.
Yes. Well.
Like in the encoding of it.
You need somewhere. This is completely to the. You need somewhere for signatures of your operations. Just assume you have a global signature of one of your operations.
Just wondering how this can, for example, implement it.
Can you go back to slide 21, please?
21.
What, 21? No, the other one, sorry. Thanks. This is more of a comment than a question. So I really like this slide because pointed out that we can see this for all abstraction, the system epsilon, right? It shows up only when it exists already in the source and system epsilon, while in system C, we abstract of these F star, just a phrase, if I understand correctly.
Yes.
So for each of the block parameters, one additional abstract that also exists in the source language. And dually, the duality is not perfect here, but dually, we see that for every single function in system at epsilon in the upper translation, we see this square modality that kind of restricts what here, right? It needs to be truthful to this. Every single function in system at epsilon, while system C, and that was originally also the point of our paper, it only shows up explicitly marked. I see in this, your work here shows really nicely. So I'm happy to. It's nice. So no question, that's a point.
Yeah, thank you.
After I have a question. Yeah. I'm curious about comparison specific comparisons with the effect handlers and whatever it is handlers. So do you think this encoding will help us compare the explicitly with the two different for example, the upper translation. Diamond, the bottom translation, and then it seems difficult to encode difficulty less using the so I'm not sure.
Yeah, I think also, there's some differences between comparing the type systems based on rules and type systems based on effects, and comparing the traditional notion of effect handlers versus lexically scoped or named effect handlers. And I think here these encodings provide some hints on the expressiveness between the type systems based on rules and type systems based on effects, based on capabilities, which is indeed that it is never obvious how to directly encode between them, because as shown by the encodings, they have quite different behaviors. But if we care about the comparison of the operational semantics of traditional dynamic handlers versus lexical scoped handlers, then I think that's a different question, not answered by this paper. But I'm suspicious about whether they're encodable at all. Yes.
I wonder. I think your next slide. So
yes.
Check handlers.
Yes. And Yes, so I'm going to talk about effect handlers now. This is a simple example of a handler for the yield operation. So for the handled computation, we yield 42 and then yield 33, and this handler handles it by just by accumulating all yielded numbers. So it will reduce to 79. Oh. So encoding effect handlers in system F epsilon is quite straightforward because both system F epsilon and MATX use traditional dynamic effect handlers, but encoding effect handlers in system C is more interesting. Yes, as we have mentioned, capability-based effect systems are typically designed for those lexical scopes or named handlers. As we can see here, this is the syntax for introducing handler system C, and we have a capability Y here, which is introduced by this handler and which is used to invoke the operations. So yeah, so instead of using do yield with some global labels, we just apply the capability Y to some arguments. And there is a semantics gap between these two different approaches. Because for dynamic handlers, there's less restriction on what you can do, so you can write more flexible programs. And with lexical scoped or named handlers, there's some dynamic generation of names in the operational semantics, which cannot be naively simulated. So in order to do so, in order to encode the handlers in system C, instead of introducing named handlers, we introduce relatively small extension of local labels with this syntax. So local ly colon into unit introduces a local label ly, which is only present in the lexical scope after in. And then to simulate the capability y here, we use this function lambda x do lyx, which just invokes the local ly operation we just introduced, and we wrap it into the modality square bracket ly to make sure that whenever we use this capability, we need to make sure that ly is present in the ambient inside context. And we pass this capability as an argument to another function, which takes a parameter y, which corresponds to the capability y introduced here. Yeah, and this yeah, and the handler still have the standard semantics, but the local label gives us the ability to generate some fresh names dynamically. Yeah, and another thing I haven't mentioned in this talk is that one of the original motivation of model effect types is to support marginal effectful programming without effect variables. So this is kind of similar to the motivation of capability-based effect systems, where we want to do higher order effectful programming without having explicit effect polymorphism everywhere. Yeah, and we also have an encoding of fragment of system epsilon without using effect variables in the target language. If you are interested in how that would work, you can go to my talk at Oxnazi Saturday. Yeah, and we also have some encodings of some other variants. So one is system chi. It is an early version of the calculus of effect, and the other is system f epsilon plus Sn, which is an extension of system f epsilon, and it's the basis of first-class named handlers in COCA. We have encoded both of them into MATX, and we have proved preservations of types and semantics for all the encodings. Yeah, and well, here are a list of insights for language designers derived from our encodings. So yeah, so this encoding formula shows that model effect types is at least as expressive as those existing systems. Yeah, and well, it is interesting future work to explore whether the other directions also work or not. Yes, and we show that with local labels, we can actually simulate limit handlers. And also, although system f epsilon plus Sn supports first class names for event handlers, which means that handler names can be passed as values, as first class values. Our encodings reveal that it is not more expressive than just having some second class local labels. Also well, in order to have some capabilities that can appear in types, we can introduce some actual type level abstractions. That will appear in types. Okay, I think I'm going to conclude. So we have two papers on model effect types. The one is in Uppsala on Saturday, focusing on how model effect types can improve practical programming with effects by not requiring effect polymorphism in most of the cases. And another is the title of this talk, which focuses on expressiveness about how we can use model effect types to have a general framework to encode and compare different effect systems. And there is some ongoing and future work. So one is we are thinking about how to do better type inference for model effect types, as well as for first class polymorphism, because I think one very important observation is that to do type inference for first class polymorphism is to do type inference for model effects is very similar to the classical problem in the literature of doing type inference for first class polymorphism, but it requires certain new things which are not supported by existing approaches, so I are exploring it. And how to make model effect types work properly with higher order effects, how to have other forms of modality elimination, relational semantics, other directions of encodings, and whether relative modalities can be used in other areas. And yeah, I think that's it. And the takeaway is to decouple effect tracking from standard type and term constructs. And by doing so, we'll have the flexibility to simulate how effect tracking works in different effect systems. And yeah, thank you. Yeah.
You may anticipate why didn't you encode capture calculus?
Yeah, I think this is very minimal field work, and I should write a paper on it.
Can I ask a question? I'm just saying.
It's romantic.
These term level mod things, they do not have computational content usually. They are just to guide the type.
Yes.
Right?
Yes.
Okay.
Well, and the point of the difference is that you probably don't write most of them. They'll get a suitably expressive difference algorithm.
Yeah.
Yeah. So I have an artifact for the Uppsala paper, but it is in a plain language. Yeah, and with some very basic type inference for model effect types. Yeah. So you need to write explicit polymorphic types, but the modality introduction and elimination can be inferred, and but it's just a toy language.
So I don't know that when I was working on, so it seems that but this we think that this one is local theoretical understanding of the differences between and also the design for the program.
Yes, yes. Well, maybe kind of both, but yes. But yeah, it's I think a main motivation is to have a better feedback system for programmers. Yeah, so type inference is kind of important if you want to.
Yeah, thank you for joining, and I'd like to thank all the speakers for the for the great talks and participants for discussions. Yeah, thank you for joining us. Okay, tonight the ICFP organized a fun performance, but it will be held in a different place. So please check out our website. Maybe and you need
Taro. Yes.
Next week.
Yeah,